Now, of course, you can find that these there are different areas of the brain from which the signals need to be tapped, but these will have different connotations as you process the signals. Sometimes in planning, problem solving, sometimes in motor control, that is the way we are moving our hands, sometimes in the taste buds, tongue, and so on. Right. Now, how to process these signals. Now, we know that there is something which is called as a continuous time Fourier transform, but if you want to analyze it in the computer, it would be extremely difficult because you have to discretize in time and frequency, right? Then only you can do the analysis. Now, of course, whenever we are doing the analysis, we would love to get the effects of the continuous time Fourier transform. So some approximations, some hypotheses, some assumptions need to be taken in order to make our DTFT or finally the DFT to give the effects of the CTFT, that is a continuous time Fourier transform. So this Fourier series defines the relationship between the continuous time Fourier transform, that is the continuous time, and the discrete frequency domains, right? And these frequency and time domains are related through the CTFT. Now, you know, whenever it's a continuous, so that means there will be integration, right? Discrete, there will be concepts of summation coming in. Now, so the Fourier transform can be written as XF, that is in the frequency domain, because you are ultimately changing it from the time to the frequency domain, and that is where the Fourier analysis becomes useful. You can write it as xt. Say xt can be, say, a EEG signal, right? This is in time domain. E to the power minus j 2 pi ft, and where f is the frequency and t is the time, dt. So all of you know, and in that way you can find out from the Fourier coefficient your original signal, which is your xt, and where of course there will be normalization coefficients, normalization constants, integral minus infinity to plus infinity xf e to the power j 2 pi ft, because this becomes inverted, so j 2 pi ft df. So that means you are getting the time domain signal back from the frequency domain using the coefficient xf, right? Now, sorry. Now, of course, we would love to discretize. We would love to discretize because ultimately we would need to work with the computer. So how about we discretize in time domain? That is, say a continuous signal is there and we sample it at specific intervals of time. That is how you can discretize in time domain of the waveform every t1 seconds. And so that xt is broken up into a number of time intervals, with each time interval depending on what is the length of the t1, and so the total length t becomes equal to nt1, right? Every individual, every t1 seconds, so it will be 1 t1, 2 t1, 3 t1, 4 t1, and so on. Of course, in this case, the frequency remains as continuous. We have to also discretize that. Now, with this, if you go to the time and in the discrete domain, that is x dtf from the continuous domain, because you are discretizing the time, right? Then obviously the integration changes to a summation sign, and the normalizing factor comes in, which is t1 here. And again, you are making your limits as n equal to minus infinity plus infinity. This, instead of t, it becomes nt, because t is equal to your nt1. So you replace just t with nt1. So x nt1 e to the power minus j 2 pi f. This t again becomes nt1. So nt1. Right. Now this dt is actually in the discrete domain. So it's discrete in time. Now, in this case, you know this this 1 by t1 is your sampling frequency, right? So obviously, say a signal has a maximum frequency component as, say, 500 hertz. So in that case, what will be the sampling frequency? obviously it will be greater than twice the maximum frequency component which you want to reconstruct back. So in this case, say it will be more than 1000. You can do it 1001, 1002, and I don't want to go into the debate how much you can go. There are also various concepts around that. I'll take it off for the time being. Let's focus on the CTFT and the DTFT. Now, obviously, you find this XDTF, which is in the discrete time, in the frequency representation, is its periodic repetition of your XF, the final XF, the coefficient which you are discretizing. In the discrete domain, the coefficient will be, it's a periodic repetition of XF. So you will find that this periodic repetition, this repetition will occur at integer multiples of the sampling frequency. So in this case, if you want to get your xt, which is your xnt, because you have replaced your small t with n capital T, because t is your sampling duration, then in that case your xnt is equal to, you are restricting within a particular frequency range. You are no longer making it as minus infinity plus infinity, right? You are restricting it with a particular range where there is some concept of truncation coming in. So, but truncation, you are doing it for the frequency, which is minus fn to plus fn, x dt, that is the discrete time coefficient, Fourier coefficient, f e to the power j 2 pi nt1, because in place of f we are putting nt1 df. So it looks like this, that there you will see that there is a periodic repetition. Now if there is an overlap at these places, then it is something wrong, then you are losing data. Now to prevent that, of course, you have a parameter which is your 2fn, the frequency should be, the sampling frequency should be the twice the frequency fn, right, which we all know. Now, and that is, in order to get your DTFT to accurately represent your continuous time Fourier transform, your XT, that is your initial time domain signal, should be band limited. So it should have a limit. And where we are telling minus fn to plus fn, it should be band limited. And that is a requirement for your DTFT to approximate your CTFT. Right, because of course you would always like to get the continuous time Fourier transform, because in discrete time you are going sampling, so you are losing some data. But for a faithful representation, you need your frequency obviously greater than equal to your fn, and we have seen Shannon sampling, right, for the time and for the choice of the frequency, particularly the sampling frequency. The same thing also holds again in the case of the DTFT being used to get for DTFT to approximate like the CTFT, because that is what we really want. But in this process, you are losing some data. So there is a problem. So how can we overcome that? There are different ways by which you can overcome. That is, what you are trying to do, you are actually discretizing. For computation, you need to discretize both the time and frequency. So if you do sampling in the time domain, it is discretizing the time, right? But you have to also discretize the frequency for you to be able to compute using the computer, right? So so in that case, we consider a fixed number of samples. That is, I'm slowly coming to windowing. And this number of samples can be finite. So I cannot tell minus infinity to plus infinity. I need to have a finite number of samples. And let us consider this total period is equal to n, which is n is the finite number of samples, and the individual duration, which is t, right? So the frequency domain can be discretized. So far we have told the small t equal to small n capital T, or you can consider in terms of P, that is total period, n times T, where n is your total number of samples, finite number of samples which you have considered. What about discretizing the frequency? For that, we know that frequency is 1 by time, right? Is inverse of time. So in this case, we can consider frequency as 1 by period, right? Which is P. in this case. But then how about in the case of time, we are doing 1t, 2t, 3t, 4t, and so on. How about in this case, we do 1 by p, 2 by p, 3 by p, and so on. So that is, you are discretizing in frequency. And so if you replace if you replace p by nt, then you are getting this as m by nt, and 1 by nt is equal to your frequency spacing in the same way we did time spacing as t1 in the initial slide. In this case, the frequency spacing will be fd, which is equal to 1 by nt, and integer multiples of that. So it is 1 fd, 2 fd, 3 fd, and so on. Very similar to the time. Now, the interesting point comes here. Now, in this process of discretizing the time and frequency, where you find you find that to get this done, you need to pay some price, and the price comes from, in order to moving, because ultimately we want the DFT, right? And so you have done DTFT as a faithful representation of CTFT, and now you want your DFT to come from the DTFT, because that is what you are able to do in your computer, right? So how can you do that? From the CTFT to DTFT, you know now. From DTFT to DFT, you have to first truncate the DFT. That means you have to restrict it within a particular window, and then discretize. That means you have to sample it. Discretize the frequency domain, right? So that means in this case, the XDFT, which will have discretized frequency, so you will not write X DTF. Instead of that, you will write X DFT MFD, which is in the frequency spacing. And then this entire thing remains the same, except that you are truncating to make it causal, that is in the positive axis, that is n equal to 0 to n minus 1. And then you are actually replacing this f by m by nt. So in this case, it becomes minus j 2 pi m n t by capital NT. So tt gets cancelled. You are getting e to the power minus j 2 pi mn by n. Right. Now, this summation is what you are actually using when you are doing your DFT. When you are using it in the, say, computer, you are writing in MATLAB FFT. You are actually doing the summation sign, right? So we will do it together. Now it's getting stuck up. Okay. Now let us see what is the effect of discretization in frequency. Say you have an original signal, which is, say, xt. You have sampled it at discrete points of time, which is xn, and say it has 0, 0, 1, 1, 1, 0, 0. This is the small window you have chosen. You do a Fourier transform, you will get a continuous spectrum, right? X e to the power j omega. So you will get x e to the power j omega in the Fourier domain against omega, right? And you will get a continuous spectrum. And then, of course, you want to go for the DFT. So discrete Fourier transform. So Fourier transform, you are discretizing. What you will do? You will actually sample, right? To get a discrete frequency domain. So if you sample it, then you will get your DFT XK, which is you are getting sample values of this entire signal, right? Now, of course, you want to get back your XM, because that is, you want to reconstruct it back. You want to know what are the frequency components, and you want to reconstruct it back. You do IDFT, that is inverse DFT. And there, the price you pay is you get replicas of the original signal. And that is where you have to use filtration to truncate, and all those things will come. So I'll not go into that as of now. So now you can see that you are getting replicas. And of course, your sampling frequency should be such that the replicas doesn't overlap, because then there is a loss of information. Now, in this case, you are seeing that in the DFT, you are getting only at discrete points, say at 1f, 2f, 3f. What about 0.5f? What about 1.5f or 2.5f? You don't have, because it's not a continuous, right? You are discretizing. So an obvious solution can be, why not you increase the number of sample points, and so that the distance in the frequency points becomes lesser. That means you are closely seeing the inner points, the internal points, right? And one way to do this is zero padding. So what you can do, you can just pad 1, 1, 0, so your average doesn't change. You pad 0 between the values, and you are, in that way you are increasing the length of the signal beyond a particular point. So initially the frequency separation was 1 by nt. Now with addition of m for mother, m zeros, you are getting 1 by n plus m times t. So in other words, the distance between the frequency points reduces. The length increases, the distance between the frequency point decreases. That means you are closely able to see, or your resolution in the frequency domain has improved. So this is a very good way by which you can catch the internal points. Now, I told that you have to truncate. You have to go through a particular window. What is the price you pay for truncating? For truncating, you will use, say, a square signal. The time is short, so I was planning to draw it, but I'll just tell you. Of course, you know a square window, right? A rectangular window, not square, but rectangular window. So when you do go in the frequency domain, it gives a sinc, right? So it will be a sinc function, a continuously extending sinc function from minus infinity to plus infinity. Now, whenever you are looking at the signal in the frequency domain or the time domain, you are looking at the signal through a small window, as if you are looking to a scenery through a small window. You are actually multiplying that signal with that window function. And multiplication in the time domain, as you all know, will be equivalent to convolution in the frequency domain. So what will happen? Because of this, you will get some additional spurious signals when you reconstruct the signal back, which you don't want, right? And that is called as leakage. And that is what is called as leakage error. So what you can do, in the case of the rectangular, so it is a sharp cutoff. How about making the cutoff smoother, which we will do in our project, small project. So you will feel that because of this, the leakage error will reduce. And how will you understand that there is leakage error? You will see oscillations in the waveform, right? So we will see through our project. So obviously, increasing the number of signal points, that is through zero padding, you cannot reduce the leakage error. You can increase the resolution in the frequency or separation in the frequencies, but for removing the leakage error, you need to use a better window, better than, say, a rectangular window. Now, why a rectangular window? It comes in case of main lobes and side lobe, which I'm not going now to those extent now, because the time is short. So we need a proper choice of window, right? Now, there is another function which is called as detrending. Say you have a signal which is shifted in the y-axis. For example, say you have a signal here, so it's the number of passengers flying through an aircraft in so many months. You see that there is it's standing on a shift, on a DC shift. So whenever we say a DC shift, that means we are introducing a magnitude at frequency equal to 0, which is not what we want. We are not interested, right? So how about bringing it down to our 0 state, so that the average of the entire signal comes as 0? And that is what is done as detrending. So if we detrend, so for that, what we need to do? We need to simply find the trend line, how this line is. So in this case, the trend line will be like this, and we subtract all the components of the trend line so that this signal comes out like this, right? Where there is no DC shift, and you have the original signal, which you can process it, right? This is in the time domain. So since time is running short, I will quickly summarize the procedural summary. The procedural summary is the procedure. How, when given a signal, what will you do? You first detrend the signal. So you will first remove in the time domain, you will remove the trend line or the DC offset, which you don't want. Then, of course, I will not look to the entire signal from minus infinity to plus infinity. I have to look through a specific segment of the window. That means, for example, say you are taking temperature data from a particular device, right? And the temperature is you are taking for the entire 24 hours. You might be interested to analyze only for 4 a.m. to 5 p.m. data. Right. So in that case, you have to look through a specific window. So multiply the signal with a suitable data window. Then you want to look to the frequency components very closely. You want to increase the resolution of the frequency components. For that, you do zero padding. This is one of the ways. There are n different ways. And then you do the DFT on the signal. So then you can apply FFT using the MATLAB. Right. So let's, so are there any questions? Quickly, I can take a couple of questions if you have any, else we'll go to the small project. Okay. So let's go to the project. Sorry. I am whatever. I think so you can see the screen now. So let us try to understand this concept through a small project, right? And this you can take as your sort of quiz also. So the discrete Fourier transform is the commonly and extensively used transform for estimating the continuous Fourier transform, continuous time Fourier transform. So from CTFT you get DTFT and then you get DFT. We have seen how of the measured signals and discrete time data. The signals measured over time and discretized are synonymously called time series, right? As one shall see, the basic characteristics of the DFT, which we have seen, produces errors. So we have seen leakage errors in the estimate of the CTFT. Fortunately, there are ways to improve the estimate very satisfactorily. There are different ways which we have learned. This notebook will show you how you can reduce these error sources, what are the correction techniques by which you can very easily get close to the CTFT. Right? This is what you want. Then it will be estimated and corrected to an acceptable level. This will establish the procedure for correctly implementing the DFT. Now to start with, let us use a function which is a sinc function. So this is a sinc function. And so the fundamental frequency is, so the cutoff exactly is the fundamental will be 0.5 hertz, let us consider. And this F0 is 0.5 hertz in the sinc T function. And so let us plot this. I think so let's all of us work together. So let's go to this function. Okay. And let me apply this. Right. So you can see that you are getting a sinc function. I have restricted within -5 to +5. Otherwise, it will be -infinity to +infinity. And this is how the Fourier transform will look like. So it's like a rectangular pulse, right? Having say -0.5 to +0.5. Now this minus is not a good thing because to realize we need it to be all in the positive axis. So we have to do something. Now let's go ahead. Now we have seen this. Now, to practically implement the DFT, we have to implement this particular function, right? The function is T summation n equal to 0 to n minus 1 because it has to be in the positive x-axis, xn e to the power minus j 2 pi mn, and then we did nt by nt. Tt gets cancelled. It is e to the power minus j 2 pi mn by m, right? This we have already seen in our previous lecture. Also, a finite duration of 20 seconds will be used. So let us use a finite duration. Let the sampling interval be 0.25, so which we have already taken as 0.25. The same thing remains. The signal and its DFT are shown in figure 2. Let's do it together. Let us do the MATLAB portion where the summation sign is being carried out. So you can see, just to tell you in short, so I have shifted it in the x-axis because it has to be all on the positive side. And then I'm using FFT because that is the summation sign which this FFT function does, this summation sign, and I have to multiply it with t, which is here 0.25, right, t. And then I'm plotting it to show you how it comes because we are using the function FFT. Now let's go to our grid. See, now we are restricting it, so it is 0 to 20, and see how is our frequency spectrum looking. So this is the magnitude. So it's a magnitude spectrum, magnitude versus frequency. Now the question is, are you seeing any leakage error between the figures 1 and 2? So obviously in this case, in the figure 1, you can see that it is a perfect, there is no oscillation here. But in figure 2, you can see there is a lot of oscillation around 0.5, effect of leakage, right? So you are seeing within a particular window. Now, now this oscillating error is the leakage error, what we decided, what we were explaining in the lecture. Now, let us try to make the signal longer. So we told that let us try to see if we lengthen the signal, does it improve? Does it help the leakage error? So what we do in this case, we use the same signal, right? And we, so now it is a 40-second signal. So 40, so we have increased it to more components, right? More, the length of the signal is increased. I hope you are understanding. If not, I will give you an exercise soon where I will not do, I'll expect you to do. Now you are seeing that there is some improvement, but still there is oscillation around the 0.5 hertz, right? So the oscillation has not totally gone away. Now, can you do for increasing it to 50%? So instead of 40, it will become 60. Try out and tell me whether your magnitude spectrum has improved. I have given you the code. Since the time is short, let me try to do it. So you see that still reduced, but still is there. Right, still it's there. So a problem. We have to do something. Now, let's try to increase rather than taking that, say we want out of 24 hours, we are taking 5 hours of data. How about we take 1 hour of data and we add zeros in between to increase this length? Let's see the effect. Right. So what we did, we appended zeros and let's see how does it come. So we append zeros and we have appended zeros. So you can see there are zeros at the front and zeros at the back. Here we have not introduced zeros in between. Zeros at the front and zeros at the back. The oscillation has reduced, but still it is there. But another thing which comes in now is this stop band portion where it is beyond 0.5 hertz, we again get some oscillation, something new, which is not what is we want. We have to remove it. Let's see the effect of sampling. What about we increase the sampling rate or reduce the sampling rate? So say in this case, so far we have done sampling of 0.25. How about we make it double, coarser, right? So say in this case, we make it 0.5. So it will be coarser. Let's see the effect, what comes. Right, it's a much coarser. So sampling rate, increasing the sampling rate or reducing the sampling rate, increasing the sampling rate comes at a cost. Because say you are using an ADC, so in that case, a higher sampling rate ADC will be costlier. So maybe the zero padding would be good, but again, you have to be very careful in using the filter so as to remove the stop band oscillations. So increasing or reducing the sampling doesn't give any stop band oscillations. So everything comes at a cost. Now let's see what is the effect of detrending and windowing, right? Detrending and windowing. So which we told that detrending is taking off the zero value, the offset, and the windowing is using a good window. So a window which does not abruptly truncate a signal. I hope you are following. I'm trying to keep time. If there are any questions, please let me know. Right. So now let us try to detrend. So the program for that, the function for that is detrend, which finds out the trend line and removes or subtracts the trend line components from the original signal. So let's try to do detrend first, followed by using a Hamming window. I hope all of you have some idea on the Hamming window. Right. So this is the detrended signal. So you see the signal is no more above. Now the signal is such that the average comes out to be equal to 0. So we have brought down the signal. So I have detrended it. Now let's try to apply a Hamming window, right? So let's see how the Hamming window looks like. So I'm using Hamming of length n. Right? So you can see the Hamming window. So it is an inverted bell-shaped window, but on a raised platform, right? The Blackman window is something where the platform is not raised. So let's see the effect, what happens. Now what you have to do, you have to look at the signal through this window. So that means in the frequency domain, you have to convolute the signal, right? So here is what we do. We convolute the signal with the original signal, and then I apply a 50 here, the summation sign, and multiplied by the time period, right? So I convolute and multiply by the time period. Sorry. So you see here what is coming. So you have detrended it. You have looked through that Hamming window, and then you have looked at the magnitude spectrum. So magnitude spectrum is really much better. But there are small oscillations here in the passband, right? But the oscillations which were there due to zero padding, those have disappeared. So the leakage error is reduced with the help of the window function by using truncation. But by using the suitable truncation, but by using a suitable window, I should say. So we have seen the effect of rectangular window, but here we see the effect of Hamming window. Now, let's compare between the two figures and see particularly what happens when we use a Blackman window. So let's try to do it together. So I have written the code for you. So the Blackman window is this. So I'm using Blackman N. Now you can see this is the original signal. The Hamming window was raised on a platform. but the Blackman window, this trend is not there. So window itself is a better one. So we should get better results. Let's see. So what I do, I again multiply this with the original signal, YD, the detrended signal. So this is the line where I'm speaking, the detrended signal with the window function, and this window is a Blackman window now. And then we apply FFT, that is the summation sign, and then we multiply it with T, same way that we did earlier. And still better, right? The oscillation in the pass band has gone, and stop band, no oscillation is there. So you can see that, of course, to make it realizable, you have to truncate, you have to use a window function, but choosing a suddenly truncating or choosing a window function that suddenly truncates a signal is not good. It will give you oscillations, which is leakage, right? Which you don't want. Now, you can choose a proper window function where the oscillations will go away, right? And you will get a much better magnitude response. Then only you can think on its IDFT, right? So your DFT should be good. And that is what we are trying to achieve. Now, let us take a signal, vibration data, and this is the exercise I will give to you. And maybe this can be taken as the quiz also, or other quizzes can be given to you based on how you are planning your session. So let us consider a vibration signal. So as an example, mechanical systems like motors or machines, they have vibration, right? And often you will find that if we do the frequency domain analysis of the signal, we can do fault finding. This is a very good way to find out machine health. So I have taken such a signal because they design either they indicate a bad design, or because something is touching some other body chassis and that's why there is a vibration, or something has been worn or something has been broken, deteriorating the chassis quality. Right, this is what we want to test. Now the frequency components are related to the type of malfunction or a broken worn part. So you know this particular frequency, okay, so that means this is the problem, so you can troubleshoot. This is a very good example where you can use the frequency analysis. Once a signal is given by vib.dat, so I have given you a vibration data. You can try to work with it. It is loaded and the direct DFT is calculated. It seems that strong frequency components occur at frequencies of approximately 1 Hz, 2 Hz, 4 Hz, and 6 Hz. Let's see it. So say we have applied at least sometime I should keep for Q&A. So say I have loaded a signal vib.dat. I have found out its length, and then I'm plotting that vibration data, and then I'm trying to find out its FFT and multiply by the T to find out the DFT. Let's see how does it come. So here is the vib.dat. So this is the vibration signal. So you can see this is the acceleration and this is the time. So this is xt particularly. Huh? So it's a time domain signal. Now I'm doing the Fourier analysis. Now you can see this one is coming round about x. X is the frequency axis. This is the magnitude. So at round about 0.76. So it's about 1 Hertz. You are getting one peak. Then around 1.5, say 2 Hertz, you are getting another peak. And say around 3.8, say around another 4 Hertz, you are getting another peak. And in and about 5.7, so around 6 Hertz, you are getting another peak. So there are 4 frequency components. Now, you can see this signal is not based at zero line. It has a drift, it has a DC shift. How about you remove the DC shift first? Maybe something close to some frequency components are coming additionally because of the DC shift, right? So how about remove the DC shift? And then how about seeing, instead of seeing the entire X domain, time domain sequence, can we see a small segment through a proper windowing function? Just the one which we did. So with a proper windowing function, first you detrend it, and then through a proper window function, you can find out the exact frequency components, right? So, Madam Dr. Panwala, so is it that we give this as a small exercise to the students, or how do we go about?
Yeah, they will try because you explained it very well.
Okay.
I must say that they must solve the problem easily, without
Yes.
any doubt.
Thank you. So I think so this is a very good take home for you. All your programs are already there. So first of all, you have to detrend. So this vib.dat, you can load it in a file, like say, and then you do detrending. So the one which we did earlier. So you first detrend and then apply windows, right? You can use Hamming window, Blackman window. I have given some examples there. You just apply that and try to see what is the frequency components. So as per my solution, the frequency components are about only two frequency components are important, say around about 0.7, 0.8, and another little bit higher, around 1.4 or so, 1.4 or 4. You can check. Um, mm, um, you can check it. I think so. With this, I keep some time, good 8 minutes of time for Q&A. If you have any questions or any hints you want on the first final part.
So any participants having any doubt can ask.
Any hint needed?
Yeah, post your question in the chat box. I will read out it.
Okay, dear. How can I?
So, okay, there is one query about the Shannon sampling theorem. Aditya, may I know from which year you are? Aditya? Madam, he wants to know about the phenomenon of a sampling theorem. How
Right,
exactly it works?
right, dear. Well, this is a very nice question, dear. You have asked. Say you are, say you have a signal, right? Now, say I go ahead with a very small thing. Say I have a line, right? And that line, I give a single dot, and I do not know what that single dot can pass through a line can pass through that single dot, a circle can pass through that single dot, an ellipse can pass through that single dot. So I don't get any idea. So then what I do, okay, let me give two dots, and then I can tell, okay, if I connect the two dots, then it's a line, right? More the number of samples, that is more the number of points, I can say, okay, this signal looks like a line. Now, let me come to the sampling theorem where, say, for example, you have a music signal, right? And that music signal you are trying to transmit from one place, from, say, you are in Surat to New Delhi. Now, in the process, you want the entire signal, if you want to pass, it will be very costly. So what you will do, you will digitize it, right? Now but ultimately at New Delhi, you want to reconstruct it back. So while digitizing, one of the first steps is sampling. Sampling in the time domain. For that, what you will do, you will say the music signal has 10 hertz, 20 hertz, 50 hertz, 100 hertz. 4 frequencies are there to make this beautiful music. Then say if you want all this to say 10, 20, 40 and 50, right? Say or 100 hertz. And say you want to reconstruct all these signals back, you want to reconstruct the entire music signal. So what frequency do you want to use it? In that case, you have to at least give 201, right? That means you are looking at more number of points. You are, say, the entire signal instead of so say this entire signal is, say this is your xt against your time, and say your entire signal is this. In that case, you will sample it, you will look at it at specific points, right? So this is what I was telling as, say, T1, 2T1, so that is NT1, right? So you are sampling it. In the same way, you can do frequency sampling. So this is what sampling which I was referring to. That means your sampling frequency should be at least greater than twice the maximum frequency component that you want to reconstruct back. I hope this is clear.
Yes, it is clear to me now.
Yes.
Any other question from the participants? So if you have any query, just post it in a Q&A. We have very limited time.
Yes.
Yeah.
And I will quickly share by the time you think, madam, if you allow me, I will go ahead and present this Karyashala brochure.
Sure, madam.
Right.
So
So
sure, ma'am. It will be helpful to students.
oh, thank you. So we are working, we are organizing a SERB funded, in fact, I am the organizer, organizing the SERB funded workshop, AI based approaches in addressing issues related to cognitive health. Right, where different types of modalities, eye tracking, EEG, GSR, PPG, everything will be sort of, there will be many speakers who will come here. So this is the, you can register. In fact, it will be a 7-day full-fledged program where you need to first register. For that, you have to give your NOC. So it's a very simple form. You have to give your NOC from the institute that you are a bona fide student there, and the institute doesn't have any issues if you join this program for 7 days, because here you have to be on campus at IIT Gandhinagar, and we will bear all the expenses of your travel, your stay, your fooding, lodging, everything for the students, and it is for the PG students. So this is the website, and here you can see that there will be many speakers here. So so many speakers are already registered, and we are updating. In fact, so there are 12 speakers, so we are updating, and there are 3 industries. Every industry will give a couple of days hands-on. One is in all types of sort of peripheral physiological indices. The biopack is in EEG and FNITs and peripheral physiological indices, and IXR labs is all in virtual reality. So these 3 industries will give a session, hands-on session. So morning will be speakers presentation, and afternoon would be about 3 hours will be the session by the industry, and overall there will be lots of fun. So
So, madam, whether the PhD scholars are eligible or not for this
Yes,
program?
yes, absolutely. The PhD students and the master students are absolutely eligible for this.
Okay, fine. So, the students who are PhD, who are doing their PhD, they need to bring NOC from where?
From their institute, from where they are doing there. So just a bona fide, this student belongs to our institute, and we have no restriction in
No,
allowing them. So that just that letter from the HOD or any person
will
whom
it
this.
sufficient if the supervisor provide the letter of NOC to them?
I think so. There is no issue because they have told it's from the institute. So they have not mentioned whether the supervisor, because it would be on a supervisor's, like on the institute letterhead only.
Yeah,
So
because
I
for the
don't think so.
university, the students, those who have registered in the university, for them it is very difficult to
Very
get the
difficult.
NOC. Yeah,
I know.
that is
I
why
know.
the letter from the supervisor can work.
Yes.
Then it's good.
Yes. 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 Absolutely, it can work, and I think so. If it is on a letterhead, would be very nice because they have not mentioned. They have told NOC from institute, so they have not told anything. I think so. We can take full liberty, and every institute, two students can come in. So this is the restriction they have told.
Okay.
Right.
Okay, fine, fine. Definitely we'll circulate because the program looks very nice and
Right.
students must have to take the benefit of this thing.
Right, and we are so close.
Yeah. Yeah. Now, any other questions
Any
from
other
the
questions?
participants? So now I think Ketki ma'am, it's a time to acknowledge madam.
Oh, thank you.
Thank you very much, ma'am, for giving a deep knowledge on Fourier analysis and its waveform conversion from time domain to frequency domain and DTFT and its inverse, and also for the examples. We would like to give you e-momento. Please have
Oh,
this.
thank you.
It's just a second. Sir, could you please make me co-host or host?
Yeah, just a minute. Just a minute.
Yes, ma'am.
Sivangi. I'm not finding you. Sivangi Vyas, okay?
Yes.
So now you are a presenter. Can share the memento.
It will be done in 2 minutes. Just come. One second.
Now you can share. Yes?
Ma'am, 1 second. No, ma'am.
No issues, dear. I'm a friend of Dr. Fanwata, so no issues. No, no worries. You can send me offline
Oh,
later on.
so sorry, madam, for the delay.
No, no issues, dear.
Yeah,
No
I think
issues.
I think you have a meeting, but really we feel very pleasure to have you in the session and
Thank you, dear.
encourage our students and motivate them to go for a deep knowledge of the
Right.
yeah, technical fundamentals.
Right. And to teach these fundamentals, I feel that otherwise it's a very dry
Yeah,
subject. But if we explain through examples and in a very jovial way, the kids will love it
yeah.
and they will be attracted to take it.
Definitely the way by which you have explained and presented, it's very nice. Even the person who is not knowing about the DFT, he can have idea. So thank you very much, madam,
Okay, dear.
on
Okay.
behalf of the whole team.
Bye
Thank you,
bye.
ma'am.
Okay,
Thank
bye
you.
bye.
Bye bye.
Bye, ma'am.
Bye.
Thank you, ma'am.
Thank you.
All the participants' feedback link has been shared in chat. So all of you are requested to give your feedback for the session 1. We will definitely start with our session 2. Meanwhile, all of you are requested, please fill the form. I think Love sir is already joined.
Yeah. Yes. So, sir, can you turn on your video?
Yes, sure.
Yeah.
Good evening, sir.
Yeah, good evening.
Good evening, sir. So, Dr. Lav Kumar sir is currently working as an assistant professor in the Department of
Sivangi, let me take this opportunity to introduce him.
Okay.
Ah, so, hello, Dr. Lav Kumar. Myself, Dr. Meeta Pawala. I'm Vice Chair of IEEE SPS Gujarat chapter. And let me give you a brief idea about this school. This school, seasonal school, is of 3 days, and this school is totally organized by the students, student branch chapters. The two student branches, GSAT and the SCAT, both have combinedly organized this event, and we faculty help them to call speakers for
Yeah,
the seasonal school. So this event is managed by them. So we must appreciate the efforts of the student coordinators and the whole team of the students. So I must congratulate all the students coordinator for such a wonderful event. So now let me start the session with the brief introduction of the Professor Lav Kumar. It's my pleasure to introduce the Dr. Lav Kumar, who is assistant professor in the Department of the Computer Science and Information System, BITS Pilani, Hyderabad campus. His current research interests are in the area of mining software repositories, machine learning, text analysis, testing of AI systems, software analytics, and social media analytics. His thesis is titled Predicting Software Quality Parameters Using Artificial Intelligence Techniques and Source Code Metrics. He has delivered more than 55 talks, and also he had published more than 80 international and more than 80 papers in international journals and the conferences. He has also published the 4 book chapters, and he is a recipient of several awards. Out of them, few are he has received the Best Young Scientist Award, Best Researcher Award, and the Best Paper Award. So, with this brief introduction of the Dr. Lav Kumar, I would like to hand over the session to the Professor Lav Kumar. So, sir, now the session is yours.
yeah, thank you, ma'am. Thank you. So first I'm going to share my screen.
Okay,
Okay,
fine.
so I think I cannot share my screen. So I think you have to make me as a
Yes.
host, yeah, host of host.
Okay, let me give you the rights.
Yes.
So, I think now you can share.
So now can you please check my screen if visible or not?
Yeah, it's visible. Now it's visible.
Okay. Okay, thank you. Yeah, so in this session, basically, we will focus on the machine learning algorithm, and mainly we'll focus on the practical implementation of machine learning algorithm, and basically for the assemble technique. But before going to start the session, first we'll discuss about the basic method, whatever we will use during this session. So first we are going through this data set that is called the Sonar data set, something related to the signal process. So I'm going to share the link in the chat box. If you want to know more about the data set, simply go through that. Okay. So this is a description related to this data set. So we will work for this data set. Now the next thing we are going to discuss about the some basic method that we can use. So as for example, if we are going to read any .csv file, here we are using one function called generate from text. So generate from text, this is just like a NumPy library function. And if you want to read the content present in .csv file, simply we will use this function. Here we have to give the file name. And if you are using the comma delimiter, we have to give the comma. Same like that, here we are also going to use some type of discretization. We are going to convert the continuous value to discrete value. And here there are different methods for.
The screen is present.
Yeah, screen is visible or not? Can you please check?
Screen is visible. Ketki madam, please mute your mic.
So here basically we have to write.
એટલે એ રાઈટ છે ને મીતા મેડમ અને અર્પણ સર પાસે છે, પણ અર્પણ સર નીકળી ગયા છે એટલે આઈ થિંક એમની પાસે રાઈટ નથી અત્યારે. તો આ સ્ક્રીન તો ઈ મોમેન્ટોની મીતા મેડમ.
Ketki madam, please mute your mic. Hello.
Yeah, so I think it's fine.
Okay.
Okay, so now we are going to use some type of discretization. So we are not going to use the continuous value. If we are going to convert the continuous value to discrete value, so here we are going to use the three different methods. One is called the uniform. Second one based on some quartile value. So we have to calculate some percentile value, and based on that we have to convert. And third one is K-means algorithm. So in this session, basically we have to use all three methods, and then we have to find, or we have to suggest to the society which method is the best for the signal processing. After that, we are also going to use some type of hypothesis test to check that whether which component of the signal is more important to decide. Here, if we are going to check, basically we are going to decide the two different problems. One is called the R signal, and second one is called the M signal. We will go through this data set, then we will get the idea. Same like that, if you are going to save the file, then we can use simply np.saveText. It will save the data in the form of .csv. So mainly we are going to use only these functions for this session, and based on that we have to develop one model using the Ensemble learning for classifying the sonar signal into the two different categories. And here we are also going to use the different type of discretization method. But before that, we are going through the Ensemble technique. Why we will use the Ensemble technique? Why we will not go to the normal classification technique? So in this session, basically we will discuss about the introduction of Ensemble technique. If we are going for the how to assemble the classification model, how to assemble the prediction model, and we will also discuss about the Bayesian boosting concept of the Ensemble. Then we will go through the performance evolution parameter, and we will discuss about some conclusion with some future work. So as we know, the performance of the data or performance of any model totally depend upon the nature of the data. We cannot claim like that one single method will always give you the best result. So here we are using the concept of Ensemble learning. If we are using the Ensemble learning in all types of scenario, it will give you the better result. We are not saying like that it will always give you the best result, but whatever the data set you are giving, in most of the cases it will give you good type of result. But when you are using some specific type of technique, what will happen like that? If the data is linearly separable, then the linear model will give you the better result. If the data is something called the polynomial, then in this case the polynomial method will give you the better result. Some case the support vector machine will give you the better result. Some case ANN will give you the better result. So why not we will combine all the technique, and we have to develop one model that is called the Ensemble learning. So in the Ensemble learning, basically what we are going to do, first, we are taking the simple base learner, like we are taking the linear regression, logistic regression, naive-based classifier. And after that, we are going to combine all the learner, and we are going to make as a simple one classification model that is called the Ensemble learning. So if the data is something related to the linear, then in this case, we are using the linear model. If the data is fit for the naive-based classifier, we will use the naive-based model, something like that we are using here. So here first we'll discuss what the different type of Ensemble learning. So one is called the based training Ensemble, major voting Ensemble, and non-linear Ensemble decision tree forest model. So we will go one by one. So first one, we are going through the major voting Ensemble. So in the major voting Ensemble, what we are going to do? We are taking the voting of different classifiers. So as for example, for a single task, we are using the 5 model. Now we are going to find out of 5 model, how many are saying like that this one belongs to the R, or simple like that we are working for the student management system, and we are going to develop one model, and that model will predict whether the student will get job or not. And we are using the 5 different type of predictor. Predictor means, as for example, we are using the placement division rate as one predictor. Then we are using the department HOD, that is a second predictor. Then we are using some professor of the department, third predictor. Then we are using the 4th year student, that is also one type of predictor. And 5th one, we are using the 3rd year student. These all are predictor because they have some experience related to the job placement. And if you are coming with your resume, they will suggest you whether you will get job or not, whether you will get a dream job or not. So if you are using the major voting Ensemble, what we are going to do? You are communicating with all the 5 models. You are communicating with the placement division head, you are communicating with the HOD, then professor, 4th year student, 3rd year student, and then you are finding in how many cases you get the positive review or how many cases you got the negative. If now assume that 3 are saying you will get the job, means you ensure that you will get the job. That is called the major voting assessment. So basically we are going to find for each model, basically we are going to find this model is saying like that whether the student will get job or not. And if it is saying 1, then we have to count as a 1 vote. So same like that. But there is something problem with the major voting assembly. What is the problem? Here we are giving the equal weightage to all the model. Means whatever the prediction weightage we are giving to the 3rd year, the same weightage we are giving to the placement division head. So that is not true, because the placement division head has 20 years of experience. Definitely he will judge more better than the 3rd year of student. But if you are using the major voting assemble, then in this case, what will happen like that? You have to give the equal weightage. But in this case, what is the problem? We cannot give the equal weightage in the. So that's why what we are going to do, we are using another technique that is called the weight-based assembly. We have to also assign some weights. So as for example, this is a placement division head. So we have to believe more on that because he had the good experience related to the placement. So we have to give the 50% weightage to the placement division head. Same like that, HOD had also good experience. So we have to give the 30% to HOD, 10% we have to give weightage to the professor, and the rest 5 and 5% we have to give to the 4th year and 3rd year. So here what we are going to do, based on the performance, based on the experience, we are giving the weightage. So that is called the weight-based assessment. That is called the weight-based assessment. Then after that, we are also going through the based training assessment. So as for example, now assume that if we are asking the question, whether I will get job in Microsoft or not. And now assume that the professor had 10 years of experience of Microsoft. Then in this case, definitely we will believe more on the professor as compared to the placement division head, because the professor has already worked for 10 years for the Microsoft and he had the good experience related to the Microsoft. So in this case, we will believe more on the Microsoft. So that's why it is called the based training assessment. So what we are going to do, first we are finding out of 5 models, which model will give the better result. And after that, we are using only those models for the future prediction. Those models for the future prediction. So if you are going through the different algorithm, this is the best training as algorithm. I have already mentioned what we are going to do. We are finding which model has the best for this data set, and we are only using that model for the prediction. So same like that, if you are asking the question related to the Microsoft, now we have to find which prediction or which predictor has the best knowledge about the Microsoft, and we have to use only those predictor for the future prediction. Next one, your major voting assemble. We have to take the simple voting and we have to give the equal weightage to the all model. We have to give the equal weightage to the all predictor, and simply we have to count how many are saying like that I will get job and how many are saying like that I will not get job. And if most of them are saying you will get job, then definitely you will get the job. That is called the major voting assembly. Now the next one, your non-linear assemble decision tree. That is the different one. I'm not going to discuss here. Okay, if the time left, then we will discuss. Okay, now we are coming to the another approach that is called the bagging and boosting approach. In the previous case, what we are going to do, we are taking the more than one model. We are taking the more than one technique. So as for example, same like that, what we are taking the placement division 8. Then we are taking the HOD, then professor, then we are taking 4th year and 3rd year student. And after that, we are joining all the model, and based on that, we are going to decide whether the student will get job or not. But in the case of bagging and boosting, now assume that if you are planning to propose one model, okay, or you are planning to propose one technique, and if your technique is not giving the better result, then in this case, how to improve the performance of weak learner, that is the task of bagging and boosting. Okay, so bagging and boosting is, as for example, if a student is not performing good in the exam, then in this case, how the student will improve the performance, that is the task of bagging and boosting. So here we will go through the bagging and boosting, and after that we will write the code for bagging and boosting. So in the bagging and boosting, what we are going to do, so as for example, first we are going to check whether the students are performing well in the exam. So as for example, the student is going for the gate exam. And now in the gate exam, we only getting the 20 marks out of 100 marks. Means if performance is not good, then in this case, what we have to suggest? What we have to suggest, how he will improve the performance? What we have to suggest? We have to suggest like that you have to do the more exercise. Okay, because if you are doing the more exercise, definitely the performance for the gate exam will. Here the same like that, we are doing the same thing. What we are doing like that, if this model is not performing better, then in this case, first we are dividing the data into the different parts. Same like that, first we are dividing the whole question into the different sets. And then we are asking the student to solve all the sets before going to the gate exam. Here we are doing the same procedure. What we are doing like that, first we are dividing the whole data into the different group, and then we are asking this model to train on this data, and then you have to find the important pattern. Again, we are asking the model to train on the second data, then you have to find the important pattern. And same like that, we are doing this process 3 to 4 times. What will happen like that, when you are going to train this model 3 to 4 times with a different set of data, definitely the performance of the model will improve. Same like that, whatever we are saying, if the student will solve 550 sets of the question, definitely the performance of the student will improve. That is called the bagging concept. But in the case of boosting concept, what we are going to do, first the student will find the idea. First the student will find the mistake. Means where we are doing the mistake in the exam. If they are doing the mistake in the database management system, we have to give more question related to the database management system. So in the case of boosting, what we are going to do, first we are finding this model is doing mistake for what types of sample, and then we are giving the more weightage to those sample. Then we are giving the more weightage to those sample. That is called the boosting technique. So the difference is only the difference between bagging and boosting is in the bagging, we have to simply create the random sets of the question paper, and then we are asking the student to solve all the question paper before going to the gate exam. But when we are going for the boosting technique, first we are asking the student where you are doing the mistake. And if we got the students are doing the mistake in database management system and Java programming, then in the next set we are giving the more question related to the database management system and Java programming. And again, after the second test, again we are going to judge where the students are doing the mistake. Then based on that, in the next test, we have to decide based on the previous test. That is called the sequential learning, and this is also called the boosting method. Okay. So the difference in the bagging and boosting, bagging is parallel method and boosting is the sequential method. Boosting is the sequential method. This is the algorithm for bagging and boosting. We will come to this point, algorithm. But before that, first we are going through the practical implementation of this classification. Okay. So I have already mentioned we are going to use the Sonar data set, and if you are going to check, this is the Sonar data set. I have already stored in 1.csv. Going to check here. This is the Sonar data set, and the last column basically contains whether this one belongs to class 1 or class 0. This is Sonar signal data set, and the last column basically contains whether this one belongs to class 0 or class 1. Now our task is to develop one AI model or one machine learning model. Based on this content, it will automatically decide whether it will belong to class 1 or class 0. Okay. And here we are using one Google Colapse. There is no need to install the Python in your system. Directly you can use the Google Colapse. Okay. So here we are going to, first we have to load the data set. So we are going to upload the data set. So we are going to the, this is our data set and we have uploaded it. Okay. Then after that, we have to check how to read the data set. This is the command that is used to read the data set. So we are going to read the data set to import numpy h mp, and then we are going to read the 1.csv. If we are going to check here, it will read the data, and after that, it will also display the data. Now you can see, if you are going to check, it will display the data. This is our data set. If you are going to find what is the size of the data set, mp.shape, you have to find, it will print the shape of the data set. So here we are working for 208 number of signals, and the total number of features equal to 60, and the last column basically contain class 0 or class 1, class 0 or class 1. You can also find how many sample belongs to class 0. Simply will find np.where data of last column double equal to 1, it will give you the number of samples belongs to class 1. So you can see, you can simply find number of sample, 97 sample belongs to class 1 and the rest of the sample belongs to class 0. Okay. So now here we have already discussed, first we are going to use the different type of discretization method, because here if we are going to check our data is present in the continuous value. So now we are going to convert this data to the discrete value, continuous to the discrete value. And there are different methods are there to convert continuous value to discrete value. I have already discussed. One is called the uniform method. Second one is called the quartile method. And third one is called the k-mean clustering method. So we have to use all method. And after that, we have to also find in how many cases. Basically, simply you can divide into the two different groups. One is lower, one or second one is lower. But we have to also find what is the optimal number of group. This data we will divide into how many numbers of group. So we will also find which group will give the better result. And we will try with the two group. So now you can see we are trying to for I a range of 0 to 10. Okay. And then we are going from the group 2 to, you can check here, we are going to use this discretization method. Yeah. So now you can see what we are doing like that. First, we are reading the data. So we are using this data, the same data, and the first we are applying the 2 plus I. So here we are using the for loop from 0 to 10. So it will vary from 2 to 3, 4, something like that. It will go from 0 to 9. So we have to write here 0 to 8. So it will go from the 2 to 10. It will go from the 2 to 10. And whatever the data it is coming, we are going to save this data in the same folder with .csv. So now we are going to write here file name equal to str of I dot so I plus dot csv. Okay. Then we are going to save the data. I have already written the command how to save the data. This is the command to save the data. So we are going to save this data and then we are writing here percentile. So what we are doing here, if you are going to check here, what we are doing first, we are reading the data, that whatever the data present in 1.csv, and then we are going to convert this data into the discrete format. First we are taking the 2 group, then we are going for 3 group, 4 group, 5 group, up to 10 group we are going to do that. And after that we are saving this data in the 2, 3, 4, something like that, we are saving the data. So now you can see if you are going to execute this code, then in this case, if you are going to check, we are getting the write the file name. So now you can see we are getting the different data. If you are going to check, if you are going to download the data.2.csv, now you can see it will divided the data into the 2 different groups. All the data become 0 and 1 because 0 belongs to 1 group and 1 belongs to 2 groups. Same like that, if you are going to download the 3, then in this case it will divide the whole data into the 3 different groups. Now you can see we are getting 0, 1, 2. Now you can see 0, 1, 2. We are getting the 3 different groups. Same like that, if you are going through the 10th one, that it will divide the data into the 10 different groups. So you can see if you are going to the 10th one, it is dividing the data into the 10 different groups. So this is just like a one type of discretization method. Once we got this value, now we are going to use the second discretization method because we have to find which one is the best for the signal processing. And here we are using the second one, quantile value. And now again, we are going to save this file from 10. 10 is I plus 11. So we are going to save this file. So now you can see the next file it is generating. If you are going to check here, now you can see we got 10 more files. And in this time, whatever the data we have generated, this data is generated based on the quartile value. Next one, we are going to use the k-mean clustering. We are using the same code. And here we are going to use the k-means clustering. We are dividing the data into the different group by using the k-mean clustering. And here we have to check 19. So here we have to write 20 plus I. So now you can see we have already completed this task. If we are going to check how many data set we are getting the total 28 data set. How we are getting the 28 data set? 1.csv, that is the original data, and after that we are getting the 9 data set, that is basically we are using the different type of discretization method. The first one we are using the inform, we have generated the 9 data, then we are using the quartile value, we have generated the 9 data set, and then we have using the k-mean clustering and we have generated the another 9 sets of data. So total we are getting the 28 data set. Total we are getting the 28 data set, same like that. Okay. Now, after that, we are going to find which features, because here we have the total 60 features are there. Can we say the all features are important to decide the signal 0 or 1, or can we say some specific set of features are important to decide the signal 0 or 1? Same like that when we have the data related to the student management system. We have the CGPA of the student, 10th marks of the student, 12th marks of the student. We have also the location of the student. Then for a specific subject, what is the grade of the student? Now we are going to find for a specific company called Microsoft, what are the important features? Whether the Microsoft will look the CGPA of the student, or the 10th marks of the student, or the 12th marks of the student, or a specific subject marks of the student. So what we are going to do, first we are finding what are the students who is getting job in Microsoft and what are the students who is not getting job in Microsoft. And then we are finding what is the CGPA of those students who is getting job in Microsoft and what is the CGPA of the student who is not getting the Microsoft. And after that we are going to find if there is any difference between this CGPA or not. If there is a difference, then we can say this is not a important feature. If there is a difference, we can say this is an important feature. Otherwise, this is not an important feature. So we are also going to use the same concept here, but we are using the ransom test, and based on that, we have to find whether all features are important or how many features are important for all data. So we are writing for I in the range of 0 to 28. So we are going from 0 to 28. Then after that, we are reading the file. So we have to write the same thing. We have to read the file. So here we are writing the file name str of I plus 1, because the file name is starting from 1, 2, 3, 4 something. So that's why we are writing here file name. So if the I value equal to 0, we are working for the file 1. If I value equal to 1, we are working for the file 2. I value equal to 2, we are working for the file 3. Once we got the data, now we are finding in how many cases we are getting the 0 or how many cases we are getting the 1. Same like that we are going to use this. So this is the index where we are getting the 0 or 1, and then we are finding the same thing np dot where we are getting the data of all column comma minus 1 equal to 0. So now first we are finding what are the ID of the student who is getting job in Microsoft and what are the ID of the student who is not getting job in Microsoft. After that, we are going for all the features. So in this case, we have the 60 features. So we are going through the all 60 features. So we are writing for j in range of 0, 60. We are going for all 60 features. And then we have to calculate the p-value and we have to store this p-value np.0 of 60. The last one is basically important. So that's why we are writing this. So now you can see we are writing for j for all feature. We are going to find what is the feature value. So we are writing data of all column comma j. What is the feature jth feature value? And after that, we are going to apply this ransom test and it will return one value. So r equal to ransom. And here we are writing what is the feature value, what is the CGPA of the student who is not getting job, and what is the CGPA of the student who is getting job. So this is called the IN. So now you can see F is the CGPA of the student. IN1 basically represent the ID of the student who is getting job, and IN2 represent the ID of the student who is not getting job. So here we are finding what is the CGPA of the student who is getting job and what is the CGPA of the student who is not getting job. And then we are going to find if there is any difference between this CGPA or not. If there is a difference, then definitely we can say this is an important feature, and Microsoft basically looking for the CGPA of the student for the placement. Now we are going to store this p value. How we can decide? P of j equal to, we are writing r dot p value, r dot p. So now you can see r dot p value basically return the p value, and if the p value less than 0.05, this is an important feature. Otherwise, this is not a important feature. So now we are going to find how many features are important. IN1 equal to in p dot, where we are getting p is smaller than equal to 0.05. Once we got all the important feature, now we are going to find data equal to data of all column IN1 of. Now we have to save this file. The same thing we are going to do here, and we are going to save this file here with 28 plus, means 29 plus something, and here we are saving the file. And we have to also find the, we are also going to print the number of features in number of important features equal to length of IN1 of G. So for a specific data set, we are also going to find out of 60 how many features have the capability to distinguish between the two different signals. So we are also going to print here. So now we have to check whether it is working or not. So now you can see if we are going to check for the first data set, only 36 feature out of 60 feature, only 36 feature had capability to distinguish between the two signals. Same like that, if you are going for the second one, after discretization, only 8 features had the capability to distinguish. If you are going to use the 3 cluster, then in this case only 22 feature, 27 feature. So here you can see if we are going to check, not all 60 features are important to decide whether this signal belongs to M or. So here you can see if you are going to check, we have generated the total 56 different data set, where first 28 basically contain the original data, next 28 only containing the important feature data, only containing the important feature data. So here you can see again, I'm going to explain you how what we are doing. First, we are using the different type of discretization method, and after that we are using one ransom test that is also called hypothesis testing, and based on that we are going to decide, whether this is an important feature or not, and if this is an important feature we are going to store the result, otherwise we are going to remove the ineffective feature if this is not an important feature. So this is the data set preparation. What we have done, we have already prepared the data set. Now we work for the model development, and here we are using the scalar different type of library. So you can see I'm going to copy paste from here. So I am planning to use these number of models. So now you can see we are using the bagging classifier, whatever we have discussed, we are using the bagging classifier. Then we are using the k nearest neighbor classifier. These are the different types of machine learning algorithms. So we are using the different types of machine learning algorithm. Random forest classifier is also one type of bagging classifier. Then we are using the extractive classifier. ADA boost means whatever the boosting technique we have discussed, that is called the ADA boost classifier. Gradient boost classifier is also one type of boosting algorithm. Then we are also comparing with the normal algorithm, normal simple algorithm like logistic regression, decision tree, multinomial Naive classifier, Bernoulli Naive classifier, Gaussian Naive classifier, and support vector machine. So we are using these number of model, and then we are going to find which model will give you the better accuracy or better F measure value. Okay. So here we are going to define the model N1, where we have to pass the training data, training actual, and testing data. So we are going to define one model. You already know if you are using the machine learning, you have to use some data for training and you have to use some data for testing. So here in this case, we are passing the training data, training actual, and then we are also passing the testing data, and this model will return what is the predicted value on this testing data. So first we are going to create one model. So we are writing model equal to, we are going to use one simple model called k nearest neighbor classifier. Now you can see how simple is that. If you are writing here model equal to k nearest neighbor classifier, you have already created the k nearest classifier. After that, if you are going to train the model, simply you have to write fit. You have to pass the training data and training actual. Now your model is trained. So in a single line, what we are writing, model equal to k nearest neighbor classifier, and then we are writing here predict fit, then automatically it will train the model, and after that we are going to find what is the predicted value. Why predict equal to model dot predict of TS data. model.predict.ts data, and then we are returning the y predicted. So what we are writing here, we are writing only 3 lines of code. The first line basically we are using the k nearest neighbor classifier. Then we are writing dot fit. Basically it will train the model. And after that, if you are writing the predict, it will predict the model is what is the predicted value on the testing data. And then we are going to return the predicted value. So now you can see this is the for the model 1. Same like that, we have to create the different types of model. Model 2, model 3. Now you can see we are simply copy paste we are doing here. So now model 1, second one we are writing model 2, model 3, model 4, and then we are writing here model 5. We are only going to change here the second model. We are going to use the logistic regression. Here we will only change the logistic. Now this model become logistic regression. Decision tree classifier, here we will only change this part as a decision tree classifier. This model become decision tree classifier. Now we have to write multinomial name-based classifier. Then we are going through the Bernoulli name-based classifier. So we have to write here Bernoulli name-based classifier. Then we have to write here Gaussian name-based classifier. So here we have to write here Gaussian name-based classifier. So now you can see if we are going to check in the simple one, this is the model 5 and this is the model number 6. Simply we have created the model. Now we are going for the support vector machine. Simply we will write here model number 7, and here you have to write this is support vector machine SVM dot SVC support vector classifier, and then you have to write kernel equal to something. So here I have already written the code. These are the different kernels we are using here. So yeah, so now you can see this is called the support vector machine with the linear kernel. We are going to use here linear kernel. Same like that, you can also use the polynomial kernel. You can also use the RBF kernel. So here you can simply write POLY polynomial kernel, and then after that you can simply write here dot. This is the model dot 8 and model dot 9. We have to write the RBF kernel. RBF. Okay. So now you can see how simply we are writing the machine learning model. First one k nearest neighbor classifier, then second one logistic regression. We are only changing this one and it will become the next model. And you can see we have written the 9 models. Simply we have written the all 9 models. In all the cases we have to pass the training data and training actual and testing data, and all the model it will return the y predicted value. It will return the y predicted value. Once it is done, that now we are going to write for the similar way we are going to write for the bagging and boosting classifier. Okay. So now due to the time bound, we are going through the same code. Same we are writing here bagging classifier. Whatever we have written here, we are writing the same thing. Random forest classifier, extra tree classifier, then AdaBoost classifier, gradient boost classifier. We are simply writing this code. In all the cases, we are simply writing .fit.tr data, and once the model is fit, after that simply you have to predict the. So now you can see once the model is fit, after that simply we are going to predict the. So here we have already written the code for all the models with the total models what we are using, the total for 13 or 14 different models we are using here. If we are going to check, the first one we are using the k nearest neighbor classifier. Second one we are using the logistic regression. Then we are using the decision tree, multinomial name-based classifier, Bernoulli name-based classifier, Gaussian name-based classifier, support vector classifier with different kernel. Then we are going through the bagging boosting classifier. Once this code is done, now after that we are going through our model development for all 56 datasets. All 56 datasets we are going through the model development. So here you can see we have also written some code here. So now you can see what we are going to do here. We are using here k-fold cross validation. Means when you are using any type of machine learning algorithm, whatever the data you are using for the training, we cannot use the same data for testing. Okay, so we always test the model on unseen data. So here we are using the k-fold cross validation. We are dividing the data into the k different parts, and at that time we are using the k-1 part for training and 1 part for testing. So we are using here 5-fold base. We are dividing into the 5 different parts. We are working for 56 projects, so we have to get the 56 different types of model with 40 different algorithms. We are getting the total 56 into 14 different models. So we are going to store what is the accuracy of those model and what is the F measure of those model. Now you can see first we are reading the data set str.i, and once we read the data set, we are going to store the predicted value. What is the predicted value? What is the predicted value if we are using this technique? So now you can see we have got the training data and testing data. Once we got the training data and testing data, we are going to store here this value into the for the testing data. So that's why we write here text index, comma, 0 equal to model. We are going to call our first model. So we are writing the model in 1. We are going to call this model in 1, model in 1. And here we are passing our training data, training actual and testing data, and it will predict what is the predicted value for this testing data, and we are going to save in the predict.. Now we have to check for the other model. We have to simply copy paste here. Yeah. So now we are going for the model 1, 2, 3. So we are writing here. And here we are going for this is a model number 2, model number 3, 4, 5, 6, 7, 8, 9. Okay. Then after that we are using total 24 models. So we have to take more. So 9, then we are using here 10, then we are going for 11, 12, 13, and 14. Okay. So 6, 7, 8, 9, 10, 11, 12, 13. And after that, we are going to store what is the actual data. So we are writing here 14 equal to TS actual. TS actual. So now you can see what we are going to do. We are using the different model, TS actual. We are using the different model, model N1. In the first column, we are storing what is the predicted value using model N1. What is the predicted value using model N2? We are going to store in the second column. Model N3, we are going to store in the third column. And what do we mean by model N3? The model N3 nothing but equal to decision tree classifier. So model N3 nothing but equal to decision tree classifier. So here we are storing the value. Once we got all the predicted value, now what we have to do, we will calculate what is the accuracy and what is the F measure of the. We are going through for J in range of 0 to 14 because we are working for 14 different models. So 0 to 14, and then we are going to store at ACB I minus 1 comma J equal to what is the accuracy score. So we are calling this function accuracy score, where we have to pass our actual data and predicted data. So what is our actual data? This is our actual data. So we are passing here. This is our actual data. And then we are passing what is the predicted value. The predicted value we are passing here. This is our J is our predicted. So now you can see the first column basically we are going to store what is the predicted value for the data 1, means what is the accuracy of the model for the data 1 if we are using the k nearest neighbor classifier. Same like that, column 2 basically contain logistic regression, column 3 contain decision tree, something like that it will store. Then after that, if you want to calculate F measure, we are also going to calculate the F measure equal to the same code we are going to also, and in this place we have to use as a F. Now we have to check whether this code is working or not. So first we have to check. So now this code is start working. What we have done here, so some warning is coming due to the logistic regression, some warning is coming. So we have to ignore it, or either you have to stop. So now you can see what we are going to do. If we are going to check carefully, we are working for all 56 data sets. How we are getting the 56 data set that we have already discussed. The first one, your original data set. And after that, we are using the different types of discretization method. And based on that, we are creating the different data set, 27 different data. Total, we are getting 28 data sets. And after that, we are using one simple feature selection technique that is called the ransom test. And based on the ransom test, again, we are generating 28 more data sets that will contain the least number of features. So if you are going to check now, you can see this code is still running. I think this code is still running. So this code is only giving some warning, but still I think completed. So if you are going to check ACB in 100, it will give you the accuracy value. So if you can see, this is the accuracy score, and we are going to save this accuracy score here, and then after that we have to check which one is giving the better result. So you can see, if I'm going to download here, download ACG, now you can see I'm going to insert here cell, insert here column, and here we are using the different types of model. So we have to try. So we are using the different model, model 1, model 2, model 3, something like that. We are using the total 14 different model. And this one, how we are getting this data set, you can also find this is the original data set. And this one, we are using the discretization method 1 with 2 cluster, discretization method 1 with 3 clusters, something like that we are using here. We are going up to 10 cluster. Okay. Then we are using discretization method 2 with 2 cluster. That is called the quartile value. Then we are going up to here. Then we are going for the discretization method 3, that is of k-mean clustering with 2 cluster up to 10. Once this is done, we are going through this one to this. Now you can see. So this is the result we are getting. Now we have to find which case it is giving the better result, which types of model it is giving the better result, because we have used the 14 different model. And if we are going to calculate the average value, you can also calculate the average value, in which case we are getting the better average, that will give you the better result. Or we can also use some type of graph that is called the box plot diagram, and here we are using some MATLAB. So if you are going to check here, ACC equal to 0. This is our data set, and then we are writing here box plot of ACC. You can see here. Yeah. So now you can see, if you are going to check this graph, this is the box plot diagram, and the model which have the higher value of this red line, that will consider as a best model. That will consider as a best model. So if you are going to check the model 1 and 8, 9, these models are giving the better result as compared to the other case. So as for example, model 1, we are also getting the better, but if you are going to check, model 9 is giving the better as compared to the model 1. So which one is the model number 9? If you are going to check which one is the model number 9, you can simply check from our code. So which model have the model number 9? So now you can see. Yeah. So model number 9 is the support vector machine with RBF kernel, and if we are going to the Ensemble learning, that is also giving the better result. So model number 10 is also giving the better result. Model 11, 12, 13 is also giving the better result. So here you can see, we can, based on this box plot diagram, you can easily decide which models are giving the better result. So if you are going to check out of all the models, model 8 and 9, first it is giving the better result. Then model number 10 is also giving the better result. Then model number 1 is also giving the better result. That is called the k erased never classified. But in this case, the sample learning is not giving that much good result. Here, the support vector machine is giving the better than any Ensemble learning. So this is our first conclusion. So if you are working for the sooner data set, and if you are using the Ensemble learning, or if you are using the normal classifier, which types of model you are going to suggest to the society? So here we are suggesting to use the support vector classifier, because if any researcher is using the support vector classifier for the sonar signal, definitely it will give the better result. Now after that we are also going to check which type of discretization method it will give you the better result. So if you are going to check here, now this is our data set, and first one is your original data set. If you are going to check, the first one is original data set, and here this is also an original data set. What I am saying. So now I am going to suggest about the discretization method. Which one is the better for the discretization method? So I am going to remove this file original data, because we are not going to compare with the original data. We are only going to compare with the discretization method. So here you can see ACC equal to 0, and after that we are going to shape this file. So here, how many discretization method we are using? We are using the 9 different discretization method. Here you can see this is the discretization method. Again, we are using this one as a one type of discretization method. So we are using here 2, 3, 4, 5, 6 up to 9. So we are using the 9 different types of group. Now we are going to suggest which types of group will give you the better result. Which types of group will give you the better result. So here you can see first we have to convert to that format. So we are taking for I equal to 1, 2. How many cases are there? 3 plus 3, 6. So for I equal to 1 to 6. Now x of, we are writing that format, x of 1 to 9 comma 14 into I minus 1 plus 1 to 14 into I equal to ACCP 9 into I minus 1 plus 1 to 9 into I comma all. So now you can see what we are doing here. Simply we have put in this value. If we are going to check, this is the second. Again, we are getting here second. Simply we are taking this one, cut, and here we are pasting here. Okay, because this one, whatever the value we are getting, that is based on the 2 cluster. This value we are getting based on the 3 cluster, 4 cluster, 5 cluster, something like that. Now here you can see if we are going to check the box plot diagram of x dash. Now you can see we are using the different cluster and we are writing here read on. Now you can see you can easily compare which one is giving the better result. So if you are going to check when we are increasing the number of clusters, this is a 2 cluster, 3 cluster, 4 cluster. When we are going for the discretization, when we are increasing the number of cluster, the performance is also increasing. At the certain instance, the performance is increasing. So this is 2 cluster, 3 cluster, 4 cluster. So when we are going for the 4 cluster, it is giving the better result. But after that, the performance remain constant. If you are going to check it, after that, the performance remain constant. So if you are going to suggest what is the optimal number of cluster we have to use, then in this case, we always suggest to use the 4 cluster, because if you are going through the 2, 3, 4, after 4, we are not getting any type of improvement. After 4, we are not getting any type of improvement. We are getting the nearly equal to similar type of result. But when we are going from the initial point, the first 2 cluster, we are not getting better result. Then 3 cluster, that is better than 2 cluster. That we are going for the 4 cluster, that is also better than 2 and 3 cluster. But after 4 cluster, the performance remains almost constant. The performance remains almost constant. So here we got the 2 conclusions. The first one we are going to suggest to use support vector classifier. And the second one we are getting, we have to suggest to use the 4 cluster, because if you are using the 4 cluster, that will give you the better result. Now the next one, we are also using the 3 different type of discretization method. One, we are using the DM1, that is based on the informed discretization. Second one, we are using based on the quartile value. Third one, we are using based on the K-mean cluster. Now we are going to suggest out of 3, which one is best? Out of 3, which one is best? So again, we have to compare. So now what we have to do, whatever the data present for the discretization method 1, that we have to put in the single column. Then here we will put the discretization method 2 and discretization method 3. So now you can see we are using the 2 different approaches. So we have to write here for, now you can see how we can write. So for I equal to 1 to 2, because we are using the original data, and second one is your reduced set of features. And we are working for 3 different type of discretization methods. So we are writing for j equal to 1 to 3. For each discretization method, we are using how many times? We are using 9 times. So we are writing k equal to 1 to 2. Then we are going to store this value in x1. Okay, because every time we are getting how many values? We are getting the 14 values. So we are writing here 14 into I minus 1 plus 14 into I, comma, sorry, 14 into k minus 1, right? 14 into k minus 1 to k minus 1, comma, I. Once you will complete the first iteration, how many value we are getting? 14 into 9 value we are getting. So that's why we are also writing 14 into 9. I will explain you how we are writing this value. 14 into 9 into I minus 1 plus this one plus this one equal to, we are going to use here ACCP. Here we are using the ACCP. The first iteration it will be 28. So we are writing here 27. So 27 into I minus 1 plus 9 into j minus 1 plus k comma all. So now you can see what we are doing here. If we are going to check carefully, okay, so here we have write I. So I equal to 1 to 2. We have to write. Yeah. So now you can see what we are doing here. If we are going to check carefully, what we are doing, this is 74%. If we are going to check here, we are getting 74%. Then 70% we are getting this one. So simply we are taking this one and we are putting in the column measure. After that, if you are going for the discretization method 2, we are getting 82.69. Now you can see this is 82.69. If we are going for discretization method 3, we are getting 78.85. We are getting 78.85. Means directly we can say this is a discretization method 1, discretization method 2, and discretization method 3. Now you can see this is the result we are getting. If we are going through the box plot diagram of x1, now you can see what we are getting. Now you can see, you can easily suggest which types of discretization method is best. If we are going to check it, in the second case, we are getting the higher value of accuracy as compared to the first one and second one. So what we are getting like that, if anyone is using the quartile value, in this case, definitely they will get the better result as compared to the inform and k-mean cluster. Because here we are getting the higher value of accuracy. If we are going to check this red line, basically representing the median accuracy, and median accuracy we are getting the higher here. Okay. Now the last comparison we are going to do like that. After applying some feature selection technique, can we say the performance of the model will improve or not? Okay. Yeah. So after applying the feature selection, because this is the result you are getting up to here, you are getting based on the original data, and after that whatever the result you are getting based on the ransom data. So now we are going to check whether the performance will improve or not. So here we have already S2. So how many data set we are using? I equal to 1 to 2, and for each one we are using 20 times. So j equal to 1 to 28 times, and then we are going to store x2 equal to 14 into j minus 1 plus 1 to 14 into j comma I equal to ACC, because first 28 we are using for original data, so I minus 1 plus j comma power column int. So now you can see, if we are going to check the x2, this is the result we are getting based on the original data, and this is the result we are getting based on the feature selection data. If you are going through the box plot diagram of x2, now you can see on. Now you can see, if we are going to check, we are getting approximately similar types of performance in the feature selection technique also. So what we can say, after removing so many features, the performance of the model is not going to be changed. If you are going to check the median value, we are getting approximately same value of median. If you are going to check here, median value we are getting approximately same. If you are going to check mean of x2, we are getting a little bit different. But if you are going to check the median of x2, what value we are getting? We are getting 76.92, and here we are also getting 76.44. Even after reducing the 50% of the feature, if we are going to check most of the cases, we are taking approximately 50% of the feature, but still we are getting the similar type of performance. This is the benefit of using the feature selection technique. Again, I am going to explain you the code. If you want this code, just let me know. You will share your Gmail ID. I will share with you. This is the same code. What we are doing like that, first we are using the sonar signal data set. Okay. This is the sonar signal data set that will contain the two different class. One is called M and R. Okay. After that, we are using the different type of discretization method. We are going to check whether the discretization method is helpful or not. And if it is helpful, then in this case, what is the optimal number of discretization? What is the optimal number of group? So here we are using the three different discretization: inform, quartile, and k-means. Out of these three, what we are suggesting to use the quartile value, because in this case we are getting the better check. If we are talking about the number of beans or number of cluster, we are suggesting to use the 4 cluster, because we are getting the better result. Same like that, if we are going through the feature selection technique, after removing the 50% of the feature on an average, still we are getting the similar type of performance. So definitely we will recommend to use the feature selection technique for the signal processing. After that, we are using the different type of classifier, but in this case, ensemble learning is not giving the better result. Ensemble learning is not giving the better result. Here only SVM, support vector machine, with RVF kernel is giving the better result. Okay, because we have also checked with the, and this one called box plot diagram. So here in the Python also you can use the py plot, and based on the py plot you can construct the box plot diagram, and based on that you can decide which one is your best. If you are going through this code, we have written very simple code here. So if you have any question, please ask. Because due to the time limit, I am not going more detail about the algorithm, because we got only 1 hour time, and that is not sufficient to cover all the bagging and boosting in detail. Okay, but I have given you the whole idea how to use the bagging approach, how to use the boosting approach. If you need the code, then please let me know. Please share your mail ID. I'm going to share it. So in the Google Colabs, directly you can share the code. That is one benefit here. So if you want to share with anyone, directly you can share with anyone, and you will get the access, and directly you can also modify the code. You can also write the code.
Okay.
So if you have any question, then please let me know.
So participants, if you have any question, please drop your question in a chat box. We are lagging behind the time because we have a next speaker with us. She has already joined the meeting. So if you have any query, please write immediately in the chat box. So meanwhile, I'm having one question, Professor Kumar. It's a very generic question. If we have an imbalanced data set,
Yes.
so what to do in such a case to train the model properly?
So if you have imbalanced data set, then in this case, you can use the different type of imbalance techniques. So like you can use the up sampling, down sampling, will also use the different variant of a smooth technique. So that will give you the better result.
So will it applicable for every kind of application, or it depends on the application? Which
No, it will not depends upon the application. It will totally depend upon the how much imbalanced data set. If you are saying like that, only 2% data containing some class 1 and the rest 98% data belongs to class 2, then in this case the smooth will give you the better result, or borderline smooth, SVM smooth will give you the better result.
Okay, and one more question from my side. So if we train the model for the medical applications,
okay,
so can we say for a single database, whatever the model is trained is a reliable?
No. So here you can use the different type of testing approach, because when we are working for machine learning algorithm, we have also tried to find the data set, the test data for which types of data your model will not work. Your model will confused. So basically you are going to find the boundary value analysis. And based on that, you are saying like that for these types of data or these types of image, our model will confuse, or our model will not give you the right prediction.
Okay. Fine.
So something like that. So if you are getting like that, one observation, if the student CGPA greater than 8.5, the student will get job. If any student is coming from 9.5 CGPA, there is no any confusion. Directly you can say like that you will get job. But if any student is coming with 8.4999, definitely will confused whether it will get job or not, because it is standing on the border point. Same like that in the machine learning algorithm. Also, you have to find those types of image which will stand on the border point. If you are slightly changing the image, the decision will change.
Okay.
Yeah.
So that affects the accuracy of the model also.
Yeah.
At last. Okay. So we have received one query from the participants. He has shared his mail ID, and he asked for your PPT as well as code.
So regarding the ensemble learning, good for regression. Yes, it is good for regression. But in the case of major voting ensemble, you cannot use for the regression purpose. You can use the average based ensemble. So you have to find what is the output of each prediction model, and then you have to take the average. That is called the average based ensemble. But weight based ensemble, based trend ensemble, you can use the same like that. Whatever we are using for classification problem, you will use the same.
Okay. One more query. This is the last question I'm addressing. If you have any more query, then you can directly contact to Dr. Love Kumar. Hope sir will give you the answer on mail also.
Yeah.
Because
So
sir,
one
we
last
have
question. Last question I'm giving. So how much percentage of data is needed for training? So previously what we are using, we are using the 70% data for training and the rest of 30% data for testing. So that is not the right approach. Currently we are not using that approach. That is also called the holdout method. Nowadays what we are using the every data for training and testing. If we are going to check here, what we are using, we are running this code 5 times. And every time we are taking some part of the data as a training and some part of the data as a testing. So if you are going to execute the code, you are using all the data as a training and all data as a testing, but you are running 5 times. So here, whatever the conclusion you are going to make, that becomes the general conclusion. But if you are using the 70% data for training and the rest 30% data for testing, what will happen like that? Sometimes it will give you 90% accuracy, sometimes it will give you 30%, sometimes it will give you 50%, something like that. So that's why we are not using the holdout method nowadays. We are using the k-fold cross validation method.
okay. And one acknowledge to you, sir. It's really a great informative session. Thank you, sir, from the participants. Okay, sir. Now it's our turn to acknowledge you, sir.
Thank you.
Thank you for accepting our invitation in a short span, and you are ready to approach us. And within a short time of period, you had given lots of information to the participants.
Yeah, that is the main challenging because I'm getting only 1 hour time, so we have to complete the code also.
And you have covered lots of methods and the comparison within an hour or
Yeah.
so. And really, this session is very helpful. In future, we hope to see you in person during the workshop. We are planning to arrange the workshop. So in that, we wish you come physically and train our students. Yes, sir. And now, at last, let me share a token of appreciation from our side. Please accept this momentum. Is it visible? Just a minute.
I think, okay.
Just a minute. Is it visible, sir?
It is coming. Yes.
Yes, it is visible, ma'am.
So just please accept it on behalf of our whole team.
Thank you.
So now we'll contact you through mail, sir. And thank you.
Sure.
Bye-bye. Bye-bye.
Thank you.
Just a minute. From where to unshare the screen? Okay, fine.
Can I start, Meeta ma'am?
Yeah. No, definitely. You can start.
Good evening, one and all. Today we are now approaching to our last session of day 1. So we have with us our next speaker, Dr. Urvashi Joshi. So myself, Ketki Patak, I am the branch counselor of IEEE SCET Engineering College. So I would like to introduce Urvashi ma'am. Before that, hello ma'am. So, Dr.
Are you calling me Urvashi? That is fine. Like,
No,
it
no.
would be much more appreciable. Please, ma'am. Please, Urvashi.
So, okay. So, Dr. Urvashi, actually, she was also our student. She has completed her MTech from SCET Engineering College itself. So, Dr. Urvashi Joshi is presently working as an assistant professor in the Department of Computer Science at Banasthali Vidyapith. She has received her bachelor degree in electronics and communication engineering in the year of 2009. She has pursued MTech, as I have mentioned, from our same institute in the field of compressive sensing. She has also completed her PhD from NIT Jaipur, Rajasthan, in the topic cluster algorithm based on social spider optimization for hyperspectral image analysis. She has published many articles in reputed journals and conferences, and her research interests resolve to obtain the solution for the problem, which is actually associated with medical signal processing, hyperspectral images, data mining, and artificial intelligence, which are already current hot topics nowadays. So we welcome you, Urvashi, for our seasonal school for the days 1, session 3.
Thank you. Thank you very much, ma'am. So I'll share my screen.
Yeah.
Just guide me through that. Ma'am, you have to give me the host rights.
Yes, Mita ma'am, would you please give her right about presenting?
Given.
Okay,
Let's
thank you.
check.
Mhm. Yeah, that's done. Just a second, ma'am.
You can just open in one tab and then share that
Yeah,
tab.
that is only I'm doing it. That is what I'm doing. I'm putting down all the tabs which are not to be shared. Still it is coming to my PPT. Okay. Yeah, ma'am, I think it's visible.
Yeah, it is visible.
Okay, so I can start rather than putting anything. Okay, so first of all, thank you, ma'am, for both of you for bringing such a warm welcome. And it is very nice to reconnect with you. Let's start with today's, it will be a sort of a discussion and the implementation along with it. So today what we're going to talk is, we're going to try to analyze again a signal, which is your EEG signals, and that is more prevalent in your medical science field. And through this signal, we try to avail certain features, like, whether you can find out that you have a depression or not, right? So today, the whole talk will be revolving around this. Now, today, if we see, the basic BCI technology, where I'm talking about, that is brain interfacing or brain communication interfacing with your other devices. So what you do is you try to collect a lot of signals that come with you, right? So these signals can be different signals which come with you, right? Maybe they would be taken as like your EEG signals or EMG signals, your brain activities or whatever. If we look into the science of brain activity, there are two types of activities that are normally felt across your brain. That is, first is when there is a movement of the electrons of the circuitry in your brain by transmission of the signals that comes across your range of the brain nerve system. And the second that comes is because of the blood flow. So whenever we try to measure any of such quantities, we take it into the momentum of bringing the signals, right? And they are firstly pre-processed, right? Now, what do you mean by pre-processing those signals? When I say pre-processing, I'll be taking three segments of it. The first pre-processing will talk, okay, because the signal is captured using different devices, or maybe the situations, there could be some noise, maybe because of my eye movement, or maybe because of my hand movement, muscular, chewing movement, etc. So that is one sort of noise that you come across. The second noise that comes is, how many channels will you take? How much data will you take? So are you going to do pre-processing in selection of the data also? Right? Then we normally talk about, let us extract features. Features means we are trying to take some information, right? That, I think the previous session was good about it. Like, you're extracting feature, you're doing any of the technology and trying to classify that. And that information is given to your different equipments that is today available in the market, that helps you to take a good decision behalf of it. So this is a basic bifurcation of your signals that can be coming into the pictures. Like, you take it into the signal, raw signal, whether you want to function on the raw signal, you want to function on the extracted features or whatever, right? So first, let us see what the signal looks like, and then we'll go into how the differentiations can be made about. So first, when I talk about my EEG signal, right? So my EEG signal is going to be something like this, right? So you have a lot of nodes. These are electrodes that are kept on your brain, right? You have a standard acquisition system for this, and your EEG comes into a segment which is of a 2D part, right? So on the top scale, you have your amplitude, right? That means you have different channels which you're capturing, and on the x-axis, you have the time domain. That means at what time are you capturing it? So this side, when I'm talking about in the y-axis, I'm talking about the spatial resolution. That means how many channels are you going to keep on your brain interface, right? And then the second is the temporal resolution. That means in time, how many sampling rate are you taking, or what is the time duration for which you are trying to capture that signal, right? So EEG signal is nothing but a simple medical text which is non-invasive in nature, means that you're not going to put anything on inside your body. It is a superficial test which is conducted. You try to just measure the different brain activities, and that is the electrical activity of your brain, right? This helps you to analyze what the different disorders that come across with it, like, seizure is there, or depression, a lot of things, sleep disorders, right? And this file which you get, it's a very raw signal which gets digitalized, right? Because we try to measure it in these with help of the montaging value. What is now montaging? Montaging means, right, you will have the reference electrode, right? So you keep a electrode, which I'll show you at the different places that we keep. So these are the different electrodes which are kept at different parts of your body, of the brain, right? So the A1 which is kept, it is acting as a reference electrode, and the rest of the electrodes are going to measure the different wave activities, right? Now, every part of your brain is firstly segmented into parts, right? So it could be like the frontal lobe, which is the first part of your brain in the forward section, right? Then is the parietal lobe, temporal, and occipital. Every lobe of the brain is going to capture certain activity, and each part of your brain has a certain role to play in the decision that you take. So for example, if we talk about any movement, hand movement or something, that is taken care by the frontal lobe, right? So that way we try to measure each and every part of the brain activity. That voltage that you get captured through that device comes into the range of about 10 to 150 millivolt, right? So it's a very small voltage that comes to you. Now what happens is that when we are trying to measure using the electrode on the superficial measure, only 5% of the signal of that voltage is also getting captured, right? So there you have to apply amplification also. Okay, now we'll move on to what are the number of the channels that are placed and how it is measured. The reason for putting onto a weightage of this is because we need to know what is the physical process going behind getting our data, right? That will help you to analyze that how will you, rectify that data, or how will you process that data on the further grounds, right? So first, how many channels are you going to use? So if we take a feature, if we take this literature, it's something about 128 channels which are allowed to be capturing. But mostly you will find a configuration which is 10 to 20 channels ratio, 10 to 20 configuration, where you keep your channels on the different parts of your brain. Now, if you see that we had already seen that what are the lobes of your brain, right? So frontal lobe is going to have all the channels which are designated or nomenclatured as F, right? Then the central part of the brain will consist of like something as a C, and the temporal will have the T part, right? And the last, which is then the parietal. The parietal will have the P, and the last, which is the end part of your brain, that has the occipital. So that is the O designation. Now, if you see, there is a bifurcation. That means all the even number channels which are there in the measuring part are coming onto the right hand side of your brain, while on the left hand side you're going to have all the odd number of the brain, odd number of the channels, right? So now we know that how the channels are placed on which part and how the nomenclature is done for each of the channel, right? Now, the activity which is captured in your EEG signal, right? That is again, like, once you have placed the electrodes, you've captured the data, you got the data into a 2D matrix. That 2D complete matrices can be again distinguished into 5 types of wave that comes as a combination. That becomes EEG, right? Along with the noise. The noise, as I told you, it could be chewing, or it could be a momentum, it could be eye blinking if I'm awake, right? So all this noise is also there, right? Along with that, you have 5 major contribution of the waves that comes into the EEG, right? The first is your gamma wave. Now, gamma waves are those waves which are actually in the range of 3 hertz to 100 hertz, right? This wave will help you to analyze how the person is able to have a problem solving capability, or what is the concentration. Now, if you see that a difference between a normal EEG and a person who is not normal, how would you differentiate? The normal EEGs are going to have an amplitude which is not going to vary vastly, a constant sort of, and a low amplification. Like, you will not have peaks in between a lot of, as compared to the person who might have some problem with respect to EEG, right? So that is how, that I'll show you in the coding part, that how we bifurcate that. Then we have the beta waves. Beta waves are those waves which are coming into the range of 13 to 30 hertz. This actually measures how much mind or how much brain is active at your end, right? Then is the alpha waves. Alpha waves are actually very helpful to, in the sleep problem, this sleep disorders. So if you're trying to analyze someone having sleep disorders or very abrupt sleep or disruptive sleep, so we always try to analyze the alpha wave that is getting from that wave, from that person, right? So that that actually reflects the restfulness of the mind, or calmness. Then you have the theta wave. Theta wave is going to give you something about how much drowsiness that person is feeling. This wave can be very helpful when you're trying to have a, driving accidents in the nights, when you're trying to, okay, someone is drowsy or not. So that you can take care by that theta wave, and you can have an alert system that, okay, with the measuring of your EEG signal, if you're having your drowsiness more, so theta wave will be more active. You can have a alert system and stop that from the having an accident, something like that. Then you have a delta wave. Delta wave is talking about, again, sleep and dreaming. So you can see that the waveforms are not at all active after beta wave. So all the activity is only restricted to the gamma and the beta waves, right? Now, I'll just talk about a brief, quick overview. What is your depression? How it is talked about today. Depression is nothing but, you have a sort of a disorder where you try to feel a sad, or, there's a persistent feeling that, okay, I'm not having interest in anything, or I don't want to do anything, or something like that. So there is a lack of motivation for anything that you come across. You have a difficulty of feeling the experience in your daily life activities. Over the time, it is found by WHO that, almost 5% of the adults that you see around have suffering from this depression. Today, this ratio is very high. As per the COVID situations, also the things have been more dismal, the workplace ratio, satisfaction. So people are more suffering from depression. Now, why would someone say that, why do you want to go from detection of depression using EEG, not, hello? Okay. So what are the common symptoms that you find in the depression? These are the common symptoms. For example, you have the brain chemistry gets imbalanced. Even your genetic and biological effects have been found over the prolonged depression existing. A lot of stress, hormonal changes are found. You don't have a proper nutrition intake, drug addictions, and a lot of things that are there. Today, if we see, in present scenario, today we see in the present scenario, then, majority of the depression detection is taken care by the psychologist. Now, what do they, how do they approach it? Like, if someone goes to them that I'm having a depression, then they will say that, okay, come, they try to analyze that person. That's the first thing that they do. If there is no EEG done for any normal, any first screening, right? Then based on their assessment of those psychologists, they try to analyze that person, right? There are a lot of surveys which are taken. Even you can find a lot of sites online which takes your surveys and they try to analyze that whether you are having the first case of depression or not. Then after if you are found that you are having a lot of depression characteristics, then people recommend to go for EG. So that is the last of the segment that come across that. Now we are moving to the code implementation for the same thing. So how can you analyze at your end the depression data using the coding section? Okay, so I'm a little bit zooming the file. So now I think it's visible.
If you can do a little bit more zooming, then
yeah, ma'am, I can do that. Yeah, I think that will be fine.
Yeah, it's fine.
Okay,
it's visible.
Okay, so now what is the aim of today? Today aim is I'm going to show you what is EEG data looking like in a digital format signal. Then we'll pre-process that data and we'll try to analyze that whether that person is going to have a depression or not, right? That is a simple takeaway from today's whole session of 1 hour. Right? Now, let us start. Whatever I have opened, it is a Colab. It's Python coding, which is supported by your Google, right? And whatever the libraries are there, that is the first segment that has been put up. So as I'm going to use machine learning, so TensorFlow will be the part of that. So that is why I'm importing the TensorFlow package as termed as TF for my utilization. Then if you are trying to plot something, so we need the plotting files also. For that, I'm importing the matplotlib as PLT for me. Then any of the numerical background that you want to do, like calculation or anything, that is supported by NumPy, right? And sklearn, again, it's a pre-processing library. Okay, so I've imported all the libraries which are necessary for me in the first segment. Now, whatever the processing that I'm doing, right now, I'm fetching my data from the drive, right? So my drive is connected to this file. That is why you're able to see the next lines of code, right? In this, what I'm trying to give them is that I'm giving them the path where my file is there. So OS path has been imported, and I'm also importing my drive. So drive content will be visible to you. Once you run this cell, right? So each cell movement is there. So I'll run the first cell for you, so you will understand. So once you run that cell, you will get any in warning, because warnings are also made on feature. So any if the warning is there, it will be printed down as soon as this this cell gets run. Right? Okay, so the first segment is run. You can see it has been ticked as green, right? Now let us go to the next cell. Next cell, what I told was we have to import the drive. So in case of drive, it will ask you that, okay, all the drive data will be available to you, right? So I'll come to this EDA file library. Okay, so it is asking you that it is connecting to your drive. So you have to give the necessary markings, permissions to be granted. So I'm allowing that, okay, please access my drive. Okay. So once you are giving your drive access, on the right hand side, these are the places you have to go to the folder set where your drive will be visible to you, right? Okay, see, drive is visible to you now. So my whole drive content is now visible to you. You can go into your drive, right? And wherever the file is existing, you can take the path of that drive from here itself, copy the path, and that path can be attached to your reading the data, right? So that I'll be showing you in the next slides, right? Now, there are two things, right? I'm importing the files, I'm installing the files, right? Now, what is the difference between installing and importing? Importing any of the packages will give you the reference of that package. You go there and access it for you. But whenever I want to install some package, that means those packages are not available in the Colab library, right? So when I'm using the MNE, right? So MNE is the package which is specifically used for your, EEG signal analysis, right? So that is why that package has been installed and not imported, right? And the rest, after installing, you import that package for you, right? Now, after the Google Drive has been available to you, you access the file. So for accessing that file, you can see that I have given the path name as raw data file, which I'm taking from the path which is mentioned here, right? So if I show you the data, how it is looking, right? So let us go to the folder which is consisting of that data. I'll tell you why to go into that data, because that will help you to understand that how the files are there. Files are named based on whether your eye is open or closed, right? So if you're doing that, when you're trying to bifurcate, right? So you will get the data in the segments like, you have your depression data, non-depression data person, then eye closed and eye open. So if you see the link here, we have taken the first as the depression data followed with HS1E0. That's the name of the file, and it is an EDF format, right? So all your EEG signals are coming into EDF files. So that is the reason why, if you remember, we had to also install PY EDF library. That is the Python EDF library supported to read any of the content which is encoded into this. Right? So this is European data format. It is just trying to digitalize your EEG signal, which is captured in the brain activity waveform, into a digitalized section, right? Into a voltage format. So first, H means it is the healthy person. S1 is the name of the subject. E0 means the eye is closed of that person. Right? So this is how you read the data. Right? Similarly, if you see, it is MDD S1 EO. That means the person, subject 1, which is having the major depression disorder, and his eyes is also closed. Right? So this is how you take the data. So both the data has been read. Right? So all the libraries are installed, the drive is mounted, the data is available. Now let us read the EDF file data. Now what is there in that EDF file actually for us? Okay. I had put while showing you by mistake, there was a space in between, so that it created an error. So now that EDF file data is available to you. Now let us see what is there in that. So after reading that EDF file, the data will be extracted from it. So you can see here channel names, right? So it is EEG, right? FP1, right? LE, EEG, F3, LE, CE. Now, as I told you previously, that the name of that channel will help us to know that where that electrode is placed. So LE means your left hemisphere, HE will be for the right hemisphere, Then FP1, that is frontal lobe first, F3 frontal lobe 3, CE central lobe 3, PE parietal lobe 3, and O1 is the occipital 1, right? So this way now we are able to comprehend that whatever the data that is coming from EDF file is also matching to what we have understood till now. you can see the total 22 channels have been measured using that file, right? This is the first file which we are reading for the healthy person, right? Then the high pass frequency that has been set. That means the maximum frequency and the minimum frequency that you're getting in that whole data set is coming as 0.5 and 80, right? Then the sampling frequency which they have used, right? For sampling the data, it's 256 hertz. Okay? The same way you will also get the data information of the EDF after reading the file which was for the major depression disorder. So here also you can see all the channel names are there. Then you have again 20 channels here. The high pass and the low pass is different and the sampling frequency is same, right? Now, next. Now I'm going to show you what is the PSD plot between, a normal EEG person and a person having a disorder, right? So first waveform is the person who is having a normal in the sense he's not suffering from the depression. So his EEG looks something like this. This has been set to a window size of 8 seconds, right? And we have picked only the first channel, that is frontal FP1, frontal parietal lobe, LE, and the maximum frequency of that has been set as 40. So this is the power spectral density of that channel only, right? The similar I'm going to plot it for the person who is having a depression, right? So the second that you're able to see is for the depression. So you can see that there is a change, right? If you see the change, there is a deflection on the initial segments of that frequency, right? So here you can see that, the curve is more on the bulging side, right? And here if you see it, it's on the lower edge, right? So there is a vast difference in the amplitude also, and also in the spectrum design, you're able to see a deflection over the time, right? Now what I'm going to do is, now because I have to give this data to some algorithm to classify for me, right? At the end, the problem is what? The classification problem. Now we have understood the data, there is difference, what is there in the data, everything is clear. Now what you want to do? You want to do is the classification. Classification at the end of the day means you want your machine to tell whether it is 1 or 0. If it is 0, you are normal. If it is 1, you are having a depression, right? So for that, I'm going to do the next steps for the preparing the data to give it into any machine learning algorithm, right? So I'm going to bring the data, right? So that raw data has been again that raw data will be fetched. So I have first brought the data which is having without depression, right? So data without depression, that data has been taken, right? Now, as we saw, there was a channel difference between the person who is having normal and the person who is having MDD. So I'm going to take equal number of channels for both the types, right? So I have taken the minimum number of the channels which are available. That was 20, right? So I've taken all the channels for the 20 channels for the person who is not having the depression, and that data is prepared, right? So once you see that data is going to look like this. Here 0, 1, 2, 3 are the channels, right? And the labels, right? So for me right now, I know that I have read this file from the person who is recorded with the normal. So there is no labels. So I'm going to append this data with the labels, right? So in that case, I'm going to give the labels to each of the recordings. So here what I can come to the conclusion is that I'm having the data which is captured for about 8,956 samples. Total duration of each file is 5 minutes, right? And it is taken for 22 channels, right? And now you can see it is in a digital format, right? Because after the 256 hertz sampling frequency, it is converted into a digital format. Now you label it, right? So after labeling it, you will get a column which is appended to it. So the labels are available for the data. Right? Similarly, the processing will also be done for the person who is not having the, person who is having the depression, right? So both the data are available to me, right? So here you can see data with depression, the labels are 1, right? And it is also available to me. Now, both the datas are there, both the datas are labeled for the machine learning. Now move on to the next step. Next step is I'm going to shuffle the data, right? Because I think the previously sir told that, we give the training and the testing data. So I have to train the machine for being non-biased, right? So when I have to make him non-biased, I'm expecting the data has to be shuffled for him. So in that case, I'm going to concat the complete data, make it a mixture of it, and give it to the your machine learning model. So the concatenation is done on this step where you're concatenating both the data which is coming to you. You're bifurcating the data which is on the EEG data label and the labels on the different domain, that is your data labels. Now come on to the processing, right? This is what you are organizing the data for machine. Till now, you have only done the organization, nothing on the pre-processing part. You took the data, you tried to manipulate the data with respect to how you like to present it to your machine, right? You made it available for him. That is what you did. Now you have to pre-process it. So what do you want to do in the pre-processing? So I'll do is the normalization. That's going to be the first thing in that I'm going to look forward to. Now, when I do normalization, I can have two types of normalization. First normalization is that I want a data which is looking into a Gaussian set of things, right? That Gaussian set will be like the data is very non-biased with a mean 0 and a variance which is more wider, right? That is one way of normalizing it. So that I'm doing it, that EG data is normalized using L2 format, right? Now, after normalizing the data, right, then I'm going to split my data into two parts. That is your training and testing, right? Here, what we have done for the right now case is that I have splitted the data into 80 and 20%, right? So you're giving the data which is 80 for your training and 20% for the testing, right? States are random. That means how the data is going to go is in the randomized state, right? That is why this normalized data are given. Then your labels are also bifurcated, training size and testing size. That is done using the sklearn model for selection, where you get your train data, right? Labels for corresponding to it, train data for test data, and the labels for it, right? So this is your concatenation of both the depression and the non-depressed. Now, so you have completed two more steps to that. After the data, then you took the data, you labeled it, you normalized it, right? And you bifurcated the data into testing and training phase. Now you have to prepare your data to be given to any machine learning model, right? Today, what I'm going to show the machine learning model is the LSTM structure. Now, LSTM structure is your structure which is right. Okay, let me show you one structurality to that. I'll just open a window. So basically, your LSTM structures are the structures which are used to, they are supposed to have a memory with them, right? So in that case, what we do is we bifurcate the whole structure into three parts, right? The first is your forward gate. Let me take some annotations. So you have something like this. The cells are there. That's a memory cell. And you try to bring a chain of memory cells. Each one is a memory cell. You try to concatenate these memory cells, right? And that becomes a long structure, right? Long structure of the memory, right? Now, first what happens is that each LSTM module is going to have three parts. The first is your forward gate, right? So forward gate, right? Then you have your decision part that you take, and the last is your output gate. So why I have used this, that was just to try the model, right? We have just tried a model to analyze it because it had a memory structure and it was many people have worked on it. So we had just tried on this. What advantage we found using this structure was that we got a good accuracy without much headache at the data part, right? Like, if you're bringing some other data or you're changing the testing ratio or training ratio, or there was also something like, that if the data is unbalanced. So all those problems which were there, we could effectively address that and cater to that needs, right? So that was a type of analyzing through the research. Okay, can LSTM come into the picture? Yes. So that was how the model was designed, right? Now, if I want to design an LSTM model, right? So I'm going to use the Keras model, right? Even TensorFlow is also available, right? This will help you to build the layered structure at your level, right? Now, as my signal is 1D, right? So my first layer that if you see in the model is the Keras sequential and 1D convolution layer, right? Then you put that, now, when you're trying to analyze the sequencing, right? So sequencing will be something like, first of all, you start with the data which is given to the nodes, right? So you will have your node structure. Then what you give it to is the convolution filter, right? As it is a 1D filter, so what I'm assuming to happen at the data side is, this is your EEG signal which is coming. So I'm going to have the filter which is going to be of 1D size, right? So here you can see that the filter, convolution filter, is taken of 64, right? Where kernel size is 7, right? Your activation layer is the red blue. So after filtration, the activation function which will be taken is the red. Then you have your size as 7. So you keep the size as 7. So now dilate the filter over the time, right? Then there is something as a dropout structure. Dropout structure is nothing, but we try to drop out the calculations, that the node calculation which was done at the previous level by 50%. That I'll show you how it happens, because every layer that you add, you're actually adding the parameters. Now, what do I mean by parameters? When you're trying to make any of the structurality, you try to have certain calculation weights, right? And that weights are actually the parameters. So people say that, okay, what is the complexity of your structurality? That is the parameters that you have to calculate, or the weighted weights that you have to update so that that machine can learn. That is the parameters, right? So every layer is going to have some parameters to be added. So of that, after convolution, I'm going to drop 50% of those parameters and take another convolution layer, which is of size 32, kernel size of 3. Right? So now you're reducing the complexity at the end, hoping you will get more better feature extracted from the previous layer information, right? Then third structure of the convolution 1D with the 16 size of 2, right? So each layer, you are dividing that feature which is extracted in the previous layer by 2, right? Then you have the now after completing the convolution followed by dropout, the third layer, that is your LSTM, right? So that comes your LSTM structure. Long short-term memory, right? So you have the LSTM structurality, which is of 32. So you're giving the sequence to it. Now in LSTM, whenever you're giving the data, it is in a format that you have to give it in the format of cells, right? For example, you have to convert that data which is there in form of vector to cellular structure, right? What do I mean by cellular structure? The cellular structure means, initially this was your size of data from 1 to 100. Now you put the data, for example, this is channel 1, right? So, and the channel 2 and so. Now you put this whole complete data, which was in the row format, into one cell. So your data will go in this size, that is 1 cross 100 into 1, right? So that is the format that goes into the LSTM structure. So that is why you are having n times steps and the feature, right? Similarly, again, another layer of LSTM has been added. Now, after that, what are you doing? After the LSTM structure, you will bring the flatten. Now, why is the flatten required? Output of the LSTM will be into a matrices form, right? That has to be brought into the flattened structure. That means you're converting one into one's cellular cell structure into 1D format, right? That is why flatten is used. After that, again, you will bring down those flatten into how much? What is requirement? What is your requirement at the end of the classification into 2? So what do I want at the end? What I'm looking forward at the end is, I'm looking at only 2 neurons. The first neuron will tell me, okay, whether I'm having 1 or 0. So, sorry. I'm only looking for 1 neuron at the output, which will tell me I'm depressed or undepressed. Then I have to follow on the previous scale, right? Moving backward tracing. So last layer will be 1, right? Because I have only to have the decision of 1 and 0. Followed by that will be a layer of 8. So you have 8 neurons, right? Followed by output of that will be 32, right? And here you have your LSTM structure, then your convo, so and so forth. And the out this side will be the input, which is your EEG signal. So this whole structure will be the machine learning model that you have made using the LSTM, right? Now you have to tell him what you're using as an optimizer, right? So you're using the algorithm, which is the ADAM, with a learning rate of 0.01, right? When I'm saying and I'm using an optimizer, I'm only trying to bring that how I'm going to learn my weight parameters, right? Then how are you going to compile the model? When I'm saying compile means I'm trying to analyze that after the data has been given, what will be the output in my case. So I'm using the functionality, which is binary cross entropy. Why binary? Because my data is in binary, 0 and 1. It's in cross entropy analysis, right? And which metric I'm using for analysis, that is the accuracy, right? So now you build the model and give me the summary of this model. So let us see what the model builds and what the summary you get. Okay, the previous is not run. Okay, I have not run many segments before also. I'm running all the segments right now. Okay, so after you build that model, so you can see here a summary has been brought to you. Now, what does this summary tell you? This end of this will tell you that what is the shape that you are inputting and what you're getting at the output side. On the right hand side column is giving you how many parameters you have to train for that layer, right? So the convolution layer is there. It is having 13 as the input. Output size is the 64. That means 64 neurons are there at the output end. How many parameters are you training? 512 weights are there in this layer to train, right? Similarly, complete information. LSTM, how many layers? You can see here, it's a very interesting to note that the convolution layer has many less number of weight parameters than your LSTM layers. So what major contribution that your weights are coming is for the LSTM. That is why it is also a bulky sort of architecture that it is taken, but it is assumed that more the weights, more the memory, right? And that is why it is having that whole structurality. Right? The last is your dense layer, right? So dense layer of 32 is having a connection of about 10,000 weights, right? And the last layers. So last layer, which is your output layer, is also having 9 weights to be updated. So in total, if you are building this model, you have weights which are trainable. It's 32,000, right? So this is what is the complete complexity of your network that you're bringing, right? Now after training, right? So what I'm printing is I have taken the model and giving it into the model name, whichever I have designed before, and fit, right? So we did two things: compiling, right? We had done the compiling phase, model building phase, right? And now we are doing the fit bit. That means I'm giving the data and asking it, what is your performance, right? So at right now, I have given the data, right? Along with the labels and the epochs, right? So how many epochs I want to do. Validation split is also given, that out of that whole complete data set, you take 20% into the validation format. So you're getting some information, right? So your accuracy is coming as 65%, 74% on the second epoch. If you keep on running, you will go to something about 98% for this model right now, right? And then your summaries are plotted. Now in the summary, what do you get is, you will get two plots. That is your accuracy of the validation as of the model after training and before training, right? So both will be there. So this is the model accuracy for training as well as the testing. The accuracy should not be like this, but it is only for the two epochs right now. That is why it is coming to you in this format, right? Same way, the loss. So you can see that over the time, the loss is on the decreasing phase, but it's not a right way to show it. So this is whole complete processing that we do, right? Now I can take the questions if it is there, or even any segment that you want me to explain it again. So that also can be done.
Thank you, Urvashi. Actually, you have demonstrated very well. So if any queries are there, first of all, let us take the question from the participant. And if they don't have, if they are not getting exactly what is the interpretation, then I have certain query from my side.
Sure.
We just wait for 1 minute if any query has been there. Okay, my question related to EEG signal analysis is what people are actually doing this analysis as right now you have rightly pointed out about depression kind of things that we are working on it. There is also certain cases in which epilepsy peoples are there.
Yes.
In which that early diagnosis are required for infants basically. So how this approach has been actually moving towards epilepsy analysis also?
Ma'am, actually, we have also gone into a lot of this. In epilepsy, what happens is there is certain, you will find certain change in EEG signals.
Okay.
Right. For example, in kids, when you talk, in that certain channels will be there, which will be showing you certain peaks at certain time spans. So when you try to analyze, so what you have to do is you have to first take that data. You try to find out that which channels for that child is actually affecting, or you can even try on the testing on a huge data set, and then you can bring down to a conclusion. Okay. Because that person was having epilepsy, that peak rose, and then that could be a decisive method. But even what I can say, what if you're working on this segment, then even you can do is ma'am, we can even take some methods like peak detection methods, and that can be also utilized.
Okay, how much important to do any data which has been there as a row, as a pre-processing part, that is that much important to give the further decision? Or we can have how many approaches we can go for pre-processing for any raw data of EEG signal?
So I think, ma'am, first question you're asking is whether is it necessary to go for pre-processing or not? Can I work on raw signal also?
Okay.
So I'll answer to that question. Yes, you can work on raw EEG also. You will see a lot of work which is done on raw EEG signal also. But in that case, what they'll do is they will take the raw EEG and they will take the methods like frequency graphs. right? For example, you will try to take the topography of that person, that which location is there in the which brain area. Even they will try to analyze the spectrum of that waveform, which is originally coming. The reason for doing that is because in our spectrum, you won't find much effective noise. You can eliminate quickly. So they work on raw EEG when they're working with any sort of spectrum analysis. But if you're doing something on direct information, like for my case, then it is better that you remove that elements and then you work. So it will purely depend like what is the next level processing that you're going to do with that data for analysis.
Okay, have you explored anything right now? We have demonstrated with the available data set.
Yes.
Have you tried with any of the data in which you are taking real-time analysis from the patient? Means, have you taken any data from patients lively?
No, ma'am, that hasn't been done yet. We have contacted few what do you say, medical firms, but still we haven't received those data into live format data that we can process. But sure, ma'am, if we will get, we'll share with you. So that
Okay.
is, we are in process because we are working. So that is, we'll be surely doing it. And that team is also working on different areas, not only on depression. Schizophrenia is there.
Yeah.
Then sleep apnea is there. So a lot of students are
Other
working on
diseases
that.
are also there. Yeah.
Yes,
Same
ma'am,
here.
that option is also there.
Okay. So thank you very much for sharing your knowledge and within a very short of time because you are also busy with lecture schedule. But thank you very much for accepting our invitation. Mita ma'am, can you share your screen so that we can just present our token of appreciation by presenting our memento to Urvashi.
Thank you,
So
ma'am.
this is our token of love to you,
Thank you,
and
ma'am.
we always believe that you would be there as a in person.
Yeah,
Because
sure,
this is
ma'am.
your hometown also. So,
Ma'am, now things are becoming difficult with a lot of responsibilities and, everyone is having different schedules. So it becomes very
yeah.
difficult to manage at both ends. But we'll surely try. Once I'll be there, I'll surely meet you all.
Okay, no problem. So, participants, on behalf of you, we thank you, Urvashi, for sharing her valuable knowledge in the domain of EEG signal analysis. There would be one feedback link given for session 3, and a quiz will be posted to your registered email ID only. So, all of you are requested to attend the quiz. There will be surprise gifts for scoring good in the quiz. So, there is a surprise for every participant. Thank you, one and all. Have a nice day. Good night. And we will meet tomorrow by 5 p.m.
Just
Thank
a
you.
minute, Ketki madam. Just a minute. I have noted the presence of IEEE Bombay section in a participant list. May I know who is there from Bombay section? Hello.
Yeah, hello, ma'am. This is Saurabh Mehta. Actually,
Okay.
this is our section's ID. I'm sorry
Okay.
about that thing.
Oh, no, it's fine. In fact, we are happy to see you over here. Just to
Yeah.
acknowledge you, I have addressed the name of you.
Yeah,
So,
thank you.
welcome.
This is a wonderful session. Thank you.
Okay, thank you, and hope to see you in tomorrow's session also.
Sure.
Okay, sir. Okay, bye
Thank
bye.
you. Yeah.
Bye.
You can also share the link to your
Peers,
Zooms
in
or
your
yeah,
peers also.
yeah, so that
I
In fact,
already did that thing. I mean, in our section, we have forwarded. I'm sure
yeah.
many students might have joined from there.
okay.
And one more thing, tomorrow we have a panel discussion on the topic benefits of the IEEE. At a different perspective, like in terms of a DLDIS talk, in terms of WISP, in terms of student branch. So every panelist will share their own view regarding these topics. So it's really useful to the section members also. So please do the publicity of tomorrow's panel discussion also.
Sure. Yeah.
Okay, and thank you
Yeah.
very much
Thank
for
you.
joining the session.
Thank you.
Okay.
So we just end up today's session. All of you have enjoyed. If any suggestions are there, you can also give in our feedback form so that we can fulfill your requirements. Every session we try with the hands-on, and tomorrow also there will be some hands-on, so you can learn better this aspect of multidimensional signal processing. Thank you one and all.
And if anyone is having a query, please raise your hand. We'll unmute you and we can discuss. Is any query to any participants? Oh, no query. That's good. So we are good in serving you the different lectures. Okay, fine. So good day and goodbye. I'll meet you tomorrow. Bye bye.
Bye.